Capacity Development Program on From Ideas to Innovation, a patent landscape approach to science and technology correlations. So friends, today we will witness two wonderful sessions on two important topics. So let us begin with the first session, and overall this will be the session number 7 of this FDP. The topic for this session is Pharma Trend Shaping Future Landscape by Dr. S.H. Pawar. And it's my pleasure to introduce Dr. S.H. Pawar, a distinguished academician and researcher with 41 years of experience. So Professor Dr. S.H. Pawar is currently working as Director for Center of Research and Technology Developments, Segal Institute, Solapur. He is the Emeritus Scientist, CSIR Delhi. He is the Distinguished Professor and former Vice Chancellor of D.Y. Patil University, Kolhapur. Sir has worked as Professor and Head of Physics Department, Director BCUD, Register of University, Dean of Science Faculty and Coordinator of School of Energy Studies at Shivaji University, Kolhapur. He has initiated and worked as founder director of 3 different multi-faculty interdisciplinary research centers at TKIT Varnanagar, Sigad Institute Solapur, and Anekant Education Society Baramati. Professor S.H. Pawar has guided 78 research scholars leading to their PhD degrees. He has published more than 1,000 research papers, contributed to 40 book chapters, edited 15 books, and 12 patents to his name. He has been featured as a top 2% scientist in the globe. He has worked as visiting professor and scientist at many universities and institutions all over the globe. His research interest includes solid state physics, material science, nanoscience and nanomedicine, agricultural nanotechnology and Ayurvedic bio-nanocompositors. Recently, he has edited 2 books entitled Silk Fibron, Advanced in Applications and Research, published by Nova Science Publishers, USA in January 2023, and another book entitled Nanotechnology Applications in Medical Plants and Their Bio-Nanocomposites, an Ayurvedic approach, published by Cambridge Scholars Press, UK in June 2024. So we are very much honored to have sir with us. So I request Dr. S.H. Pawar sir to deliver his session. Over to Dr. Pawar.
Good evening to you. Am I audible?
Yes, sir, you are audible.
Yes, sir.
Okay. Now I wanted to share my slides. So PowerPoint presentation.
Yes, sir, it is visible.
Yeah, you have got it?
Yes, sir. Yes, sir.
Okay, now the PowerPoint presentation. Okay. Good evening to you. Friends, first of all, let me thank the organizing committee for giving me this second opportunity to make the presentation in this ATAL FDP program. Friends, in my first talk, you know that I have talked about the science and technology roadmap. And in continuation with that, in this today's lecture, I'm going to, that is pharma trend, that is shaping the future landscape. Specifically, in my first lecture, if you recollect that the picture which I had shown, that was the Sinhagad Institute, Solapur, where presently I am working. And you might have noticed that there were the clouds over the building, and our main focus of the research at the Sinhagad Institute was the cloud precipitation and study the rainfall and artificial rain. Here you can see that the picture in this picture, it is a picture of the institute where I was working as a vice chancellor for 10 years. That after completion of my tenure as a professor, I head of the physics department in 2006. I could I got the opportunity of to be a vice chancellor, a founder vice chancellor of the 25 years old medical college, D.Y. Patil Medical College in the Kolhapur itself. And after serving 37 years in the Shivaji University as a professor of physics and material science, then I was appointed as a founder vice chancellor of a new university, which is a medical university. Now here in this picture, you can see that this is the hospital of D.Y. Patil University. This is a 800 bedded hospital, 400 MBBS students, then 400 MD and MS students, 400 doctors, and in continuation with this, in order to prove the establishment of the as a university, because college there was not much research, but in order to establish as a university, the research components must be a very strong component, and that's why I established in this medical university the Center for Interdisciplinary Research, where the doctors, engineers, and scientists they must come together and do the work. So here in my presentation, I'm going to talk on pharma trend shaping future landscape. When this university is a medical university, and you know that it is mainly we are treating the patients, and you know that to treat the patient, we need the medicines. And then in order to know, so my students studying in this university, they were MD, MS, and MBBS students. So they must know about the medicine. So here in this talk, I'm going to make the presentation specifically pharma, which is the tablets, medicines, which is needed for the patients. So the focus of my research, specifically, okay, training is one part and the research is another part. So to establish the existence as a university, there must be a strong component of the research. And so I started a PhD program in the interdisciplinary area, specifically with a focus on the medicine. And so in this particular talk, I'm going to talk about what are the new trends in pharma, what is new trends in medicine, so that the pharma people, pharma industry, they have to orient it as per the need of the time. And for that purpose, here I focused about PhD program, specifically arthrodesis and nanotechnology, because you know that the present century is the century of nanoscience and nanotechnology. And so the application of the nanomaterials, there are so many applications. In my last lecture, I mainly focused on application of nanotechnology in energy or top 10 problems, specifically energy, environment, water resources. And here in this lecture, I'm going to focus on the application of nanotechnology in medicine. Now here, so our PhD program, initially, focused on the atherosclerosis and application of nanotechnology, cancer nanotechnology, stem cell nanotechnology, wound healing and nanotechnology, in vitro and nanotechnology. So these are the focus of our PhD program in this thing. Now, before starting this particular program, being a medical university, so we must, see what is the, focus, or what is the statistics, or what is the, prediction of the WHO, that the World Health Organization. So all the medical institutions, okay, they are expected to start their research as per the need of the, WHO, so World Health Organization. If you look at the World Health Organization, this is, I mean, loaded, but more or less the similar the trend observed in case of WHO report. Specifically, there are two types of diseases: communicable diseases and non-communicable diseases. So when we look at the, I mean, medicine, so communicable, non-communicable diseases and non-communicable diseases. In non-communicable diseases, specifically, if you look at the, I mean, the kill that is due to the, I mean, that non-communicable disease, 38 million people each year. Similarly, so it is a very, very large number. So whatever medicines so required or to cure the patient, so it is very, this is a thrust area. Another thrust area is non-communicable diseases include, what are the, I mean, if you want to go on micro level, as per the WHO report, micro level, the non-communicable diseases include cardiovascular diseases, cancer, chronic respiratory diseases, and diabetes. These are the main diseases under the non-communicable disease. Especially in cardiovascular diseases, accounts for most deaths, 17.5 million people annually. Of course, this might plus minus will be there, followed by the after atherosclerosis, after heart attacks, there are maximum number of deaths in the cancer, 8.2, and the respiratory diseases, 4 million, and diabetes, 1.5 million. This is the status of the communicable, non-communicable disease. On the other side, there's a communicable disease where the pharma trend has, I mean, modified, changed according to the need of this. So communicable diseases, you know that the tuberculosis is one of the pretty long time. But recently, we know that whole world has, I mean, faced specifically viral infection and specifically the COVID-19 diseases. So we thought that let us concentrate our research on this area, and specifically, as I told you that the 21st century is the same century of nanoscience and nanotechnology. So in this sense, the medicine field has also, has quite importance, specifically the new trends in pharma, that is the nanomedicine is a very, very important branch of the, I mean, medical sciences. Specifically, if you look at there are these particles, nanoparticles, and nanomedicine, they are made with the nanoparticles. So viral particles, so depending on the side, you know, the viral particles, then polymeric nano carriers, drug conjugates, similarly, inorganic nanoparticles, lipid nanoparticles. So these are specifically when you go for the medicine, when you go for the pharma industry. So, and then specifically the new trends, I mean, the areas that are coming up. So accordingly, the pharma people must also change their trend. So this is very, very important for the nanoscience. So in case of the nanomedicine, so in my talk, I'm going to focus on the new trends of pharma related to the nanomedicine. I do not know to, because I will not be able to cover all the things, but I'm going to cover here what are the recent developments, what are recent things, specifically the nanoparticle, nanomedicine. Here, nanomedicine is a branch of medicine that applies the knowledge and tools of nanotechnology for the prevention and treatment of the disease. And similarly, the nanomedicine involves the use of nanoscale materials such as biocompatible nanoparticles and nanorobots for diagnosis, that is for the delivery, sensing, and actuation purposes. So here you can see that a nanomedicine, a typical example, I'm giving the typical example of C60. And you know that there are different atoms they are there. And you can see that the nanomedicine and nanotechnology journal, this picture is there. Here you can see all these things are the atoms or this is a big molecule. And here in this, there's one new atom has been added. So it means that we are making, so this is nothing but addition of some foreign atom into the original molecule. And so this type of material is called as a nanocomposite, and that is specifically bio-nanocomposite. It means that when the nanoparticle they are added into the biological material, so it becomes the nanobiocomposites. and specifically the properties of original nanomaterials, and then if we make it as a that biocomposite, adding some foreign atoms or foreign molecules in that, depending on the what kind of biomaterial, what kind of particles or atoms you are adding. So these bio-nanocomposites, there are a variety of bio-nanocomposites. So then the medicine, so specifically bio-inspired rosette nanocomposites, similarly graphene enhanced polymeric nanoparticle. So it means that this was the medicine, the polymeric nanocomposites loaded with polymeric nanocomposite loaded with the nanoparticle. Similarly, mechanical strip and interpreting new nano works, and specifically controlled hydrogel nanocomposite. So these are the variety of bio nanocomposite. Simply nanoparticle will not act as a maybe as a medicine, but if you could make the combination that is embed in nanoparticle into the biomaterial, so one can make the bio nanocomposite, and the properties of the bio nanocomposites are altogether different than the basic properties. So when we are talking about nanomedicine and the biocomposites, we must know exactly who is the person who has worked on the nano. And you know that the size of the nano 10 to minus 9 meter into the meter. And so that is on 20. So the first person that is who is responsible for the development of all the the nanoscience and nanotechnology in all branches, not only the medicine, not only the healthcare, but it has the nanotechnology has made a key role in a variety of disciplines. So on 29th December 1939, Richard Feynman presented a visionary and poetic lecture at the meeting of the American Physical Society. Friends, I am very happy that the physics person who developed this nanotechnology, and I'm glad that I am basically a physicist, and I have done a lot of work in nanoscience, nanotechnology in my earlier university, Shivaji University. So after doing a lot of research in nanomaterials and material science, when I joined this particular D.Y. Patil University, which is a basic medical university, so then we concentrated further on the nanoparticle, nanomedicine, nanoscience. So in his lecture in 1959, Richard Feynman, when he gave the lecture, there's a plenty of room at the bottom where he speculated on the possibility and potential of nano-sized materials. So this is you must know this thing. So when you talk about the nanoparticles and technology, so chemistry, condensed matter, but what chemistry they do, less side, they go, from the atomic size, which is less than 1 nanometer. Because we said that 1 nanometer is 10 to the minus 9 meter. In case of condensed matter, they talk about the particles, and particle size greater than 100. So if you look at the chemistry deals with the science of less than nanometer. Physics, they study the material which is greater than 100. But in between 1 nanometer to 100 nanometer, there is a range. That is basically range which were ignored, was not much studied, and it's only because of this size particle cannot be seen by vision. So as soon as there is the research in observation of particles, that is the electron microscope and all the things. So this branch we could do this thing. So when you talk about the nanotechnology, specifically pharma industry, they must be trained and get educated. Because we are talking about the nanomedicine, specifically for the healthcare. So here you can see that a study of that it involves basically the nanomaterials and the nano devices, then nanocrystalline and nanostructured material. Similarly, names in case of nano devices, MEMS, and then that is respiratory types, and then micro arrays. So these are the two different branches of the nanotechnology in case of nanomedicine. In case of nanostructure, you can say polymer material and the non-polymer material, depending on what kind of materials you are using. And these nanoparticle, dendrimers, and these are the different things they are there. Now here you can see that this is 1 meter, and then these are the 10⁸. It means that this 1 meter is 10⁸, or 1 nanometer 10⁻9 meter. So in case of pharmacological nanotechnology, you can at about this diameter, the dendrimer, nanotubes, quantum dots, they are available in 1 nanometer. 10⁻10 nanometer, there's polymer nanoparticles, then missiles, these things. In this other range, that is microparticles, and then here tablet capsules. So here we are doing this, but in this tablet capsule, they are made with the nanoparticles. And so it is the very important property. So these are you can see the organic nanoparticles, and then here it is, you can see utilization of the nanoparticles in nuclear medicine. So these are the different things. So DNA and so micro level virus and these things. So here and there, here you can see the dimensions as per the different materials. So DNA, this is the 1 nanometer, they are there. And so here you can see different nanoparticles we are being used in this thing. Specifically, when I joined this D.Y. Patil University and I started research on the nanomedicine application of the material science, nanomaterial science, and then I have done a lot of work in Shivaji University, and when I joined the D.Y. Patil University. So based on my experience with my PhD students, as I told in the last lecture, that I produced 52 PhD students in material science in Shivaji University and 26 PhD students in D.Y. Patil University, which are nanomaterials, nanomedical application. And I have written a book, that Progress and Prospects in Nanoscience Today, the Shivaji Power, and this book is published by Nova Science Publisher, USA 2020. So most of the research that I'm going to touch, generally I give the lecture, not just by copied material, but I give the lecture, that's what I have done, what my PhD students have done for their research. So based on the research that I have done in the D.Y. Patil University, and based on the background which developed the material science, nanomaterial science in Shivaji University, I have written a book, and this book has been published by Nova Science Publisher, USA. So based on that, I have given many, if you can go through this particular book, and you will find that application of, so here in this lecture, I'm concentrating only on this medical healthcare application. There, as I told you, that the nanoparticles, now they have the application in energy, environment, something. But here in this particular speech, I'm going to talk only on the applications of nanomaterials for healthcare development. So here in case of healthcare development, so nanotechnology, so you can see that the different applications of the nanotechnology, and I don't want to repeat it again here, this thing. And then here from up till now, what I have told about this nanomedicine, you might have noticed that the nanoparticles is very, very important base, or the base for your pharma industry. So synthesis of the nanomaterial, the specific very important property of the nanoparticle, because when you try to apply the nanoparticle, nanoscience for the medicine, everybody must know that the size, as per the properties of the nanomaterial, they are very much dependent on the size of the particle. So it means that whatever tablets you are preparing, whatever medicines you are preparing, so you must control the size of the particle, because the size of the particle may be 50. Suppose you have prepared a powder, maybe the nanopowder, and the size is suppose 50 nanometer. So you suppose one batch of the medicine, you have prepared 50 nanometer. And suppose by mistake, if it goes from 55 nanometer, the properties of 50 nanometer nanomedicine is altogether different than the properties of 55 nanometer. So it's very important that when you deal with the pharmacy, nanopharmacy, or maybe pharma industry medicine, controlling the size of the particle is very, very important in the range of the, because, for example, suppose if you consider the gold nanoparticle, the gold particle, the melting temperature of the gold may be 1060. But if you reduce the size and color, you know that beautiful color, yellowish, shining color. But if you go on reducing the size of the gold from macro to micro to maybe nano, and in nano from 100 nanometer to 1 nanometer, this particular range, very, very sensitive range for the size, you will see that the property they change, like the color, yellow color of the, the gold becomes maybe the red and violet as when this. So it means that simply gold is, but simply gold is not important, but what is the size of the gold is very, very important. Specifically, the exactly same thing. If you are treating the patient with a tablet having the 15 nanometer diameter, and if the unfortunately the same material, same chemical, but if the size is maybe 60, you will get different result. You will not get the reproducible result. So in so pharma industry, especially when you go for the nano medicine, nano tablets, it's very, very important to go for monitoring or controlling the size of the particle. The question comes here, now let's start how to make in pharma industry, how to make the nano medicine. So the first is that the material must be in the range nanoscience. That is from 100 nanometer to 10 nanometer. Another very thing that is that same chemical, but you must then control whether you want it to 40 nanometer or 50 nanometer. If you, the same material, gold is there, maybe or any medicine is there, but if there is slight change in the, diameter, you will not able to get the reproducible result. So, and how to make the nanoparticle. So there are two types of these nanoparticles can be made by top-down approach and bottom-up approach. What do you mean by top-down approach? Top-down approach means suppose you have a big, this is a macromolecule, this bulk material, and then go on thinning and thinning and thinning till you get the size from meter to centimeter to millimeter to micrometer and then nanometer, then 100 nanometer, maybe 50 nanometer, 10 nanometer, so like that. So that is that which is called as a top-down approach. We are going from large size to the lower size, and in the lower size, when you reach to the diameter, maybe in the range of 100 to 10 nanometer. So that is the process. That is the one method. Second method, which is called as a bottom-up approach. What it means, bottom-up approach? It means that we have the atoms and molecules. Then put the atoms and molecules together. As I had seen earlier figure, in case of chemistry, because the bottom-up approach, specifically you have the chemicals, and these chemicals may be the atomic size. So when is one atom, two atom, the diameter of the atom may be as angstrom, and minus unit then. So one atom, two atom, and so you can transfer from the one angstrom to the 10 nanometer. So it is called as a bottom-up approach. So this is the how to synthesize. So when the pharma industry, they must be made aware of so this basic thing. Otherwise you will not be able to produce the proper medicine. So what are the recent trends specifically in the pharma industry? When you go for the nanomedicine, specifically the nanomedicine, the same material, if it is prepared in the nanomedicine, the same material which are using for the patient, treating the patient in the micron level side, and the same material, if you could make use of that nano side, you'll find tremendous benefits with this thing. So that's why it is going from the macro molecule medicine to the nano medicine is a very, very important aspect of this thing. Now, specifically, what are the methods? Now, when I go but start the nano medicine industry, so then we must know that. So how these different methods? So chemical method, physical method, and biological method. So materials can be made, nanomaterials can be made. So these are the three different categories. Specifically, the materials made with the chemical, materials made with the biological materials. So depending on the property, depending on the method, which method you are using. So it's a very important. Maybe the same material was prepared by three different methods. you will find that the properties are different. So depending on the requirement, you have to select that which method you have to select. In pharma industry, selecting of these things is it. So specifically in my university, when I was the vice chancellor for 10 years, as I told you that we had the 600 MBBS students, 400 MBBS students, and 400 doctors. So and then interdisciplinary research, bringing doctors, engineers, and scientists together. So I have found center point research. In center point research, we have made the variety of nanomaterials which are related to to prepare the medicine. Specifically, these are the materials that is MgFe2O4, NiFe2O4. These are the materials that is, these materials we have prepared and studied for their medical applications. I will give you later on what are the medical applications that we have studied for this thing. Now, specifically, we have concentrated on the rather than physical methods or chemical methods, we are concentrating on biosynthesis methods because ultimately these materials which are prepared for the biological thing and or for the healthcare, the biology. So there's a good match between that's why we concentrate on more weightage for biosynthesis nanomaterial. And in case of biosynthesis nanomaterial, so pharma people must know the biosynthesis. And biosynthesis, extracellular synthesis. So new trends in the pharma. So so especially bacterial medicinal, fungi mediated, bacterial, one can prepare the nanoparticle using the bacteria, one can prepare the nanomaterial by fungi, yeast, and then virus, plant. So these are different methods. So they are there to prepare the nanoparticle. Here I give the example of the project which I have sanctioned from the DSC, Department Science and Technology. The studies on synthesis of COFE2O4, as I told you that earlier, the what nanoparticles were prepared. So here, order to suit the research in medical research in the DY Patil University, studies on synthesis of COFE2O4 magnetic nanoparticle using magnetotactic bacteria. As I told you that the method is the bacteria making with the bacteria, one can make the particles. So here, this is a project. I got this sanctioned this particular project from the DST and so submitted to Government of India, Ministry of Science and Technology, Department of Science and Technology, the Technology Bhavan. So this was so here the why as I told you that physical method, chemical method, and biological method. So why microbiosynthesis? Why I selected? So you can see that, as I told you that the property of the nanomedicine that are very sensitive to the diameter. So here, narrow size distribution. Now, suppose we prepare chemical method, what happens? Suppose we prepare the method, a particular medicine, and if you plot the graph of diameter versus how the particles they are there. So we get the Gaussian curve. It means that the broad Gaussian curve, the material is the same, but the distribution of the diameter is very different. And you know that as in case of nanomedicine, if there is change in diameter particle, property will be different. So you will get the mixture of the property. So it means that there should not be the Gaussian curve from the broad distribution curve, but there must be the narrow size distribution. It means that if you are preparing the nanoparticle, it must be, the size must be between 50 nanometer plus minus. It should not be vary from 30 nanometer to 60 nanometer, 70 nanometer, and with a peak at the about maybe the 50 nanometer. And so it is very essential. But by making the microbiosynthesis method, this is a very, very fantastic method. That is narrow size distribution, which you can get the reproducible result. So for medicine, because it's very important to get the result, is very important. Then secondly is that this material must be the crystalline. The nanomaterial which are getting this, it must be highly crystalline, prepared by the microbiosynthesis rather than chemical or physical synthesis. So that's why we prefer, that is specifically in my university, we concentrate on the microbiosynthesis of the nanoparticle and then better shape control, that is monodispersive, specific size range it is there, biocompatible, biodegradable, and then bioinspirable, eco-friendly route for this thing. So depending by that time, then we got this thing. Now, specifically, I'll give a typical example of the biosynthesis of nanoparticle, nanomedicine, which we prepared, studied with the help of, I have prepared so many other, using so many methods, but I'm concentrating here, giving one typical example, of the bacterial synthesis of nanoparticle by using the bacteria. Here, specifically, we have considered magnetic bacteria, and that is one of the nature's miracle. Friends, you know that magnetotactic bacteria, it means that this bacteria has the magnetic property. So why that this bacteria has magnetic property? You can see that here the bacteria, and you can see here the black dots, they are there, black there. So these are the magnetic they are the P2O3. So magnetotactic bacteria are microorganisms that belong to the heterogeneous group of gram-negative bacteria with the diverse morphological activity. Now, the magnetotactic bacteria, they are specifically at the bottom of the lake. You find that in the mud. And because we know that the earth, the North Pole, South Pole, and it's the North Pole. So where you are, whether it's in the upper part of the earth or lower part of the earth, depending on the magnetic effect. So these bacteria that orient migrate along the magnetic field lines using intracellular magnetic structure called magnetosome. So you can see the magnetosome. Their magnetosomes are nanometer sized, which contain crystals of the magnetic mineral. It means that in the nature, there are the magnetotactic bacteria, and these magnetic bacteria are at the bottom of the lake, in the mud. They are there. So we selected that this specifically this. So we just bacterial magnetosome. So we desynthesized this. We got this. So these are different magnetosomes, and with the different diameters, they are there. And this where from? It's a very interesting story. That two of my PhD girl students, they were working, working for this synthesis of magnetotactic bacteria because they are familiar with the bacteria. So we selected the synthesis of the nanoparticle rather than other chemical or physical. We selected the biosynthesis magnetotactic bacteria, and that's too specifically natural bacteria. Now you can see that. You know, that since it was this work that I was earlier 50 years in Kolhapur, and those I don't know in Kolhapur, I think those who have visited Kolhapur, there is the attraction that is the Rankala Lake. So here is the Rankala Lake, and from the Rankala Lake, at the bottom of the Rankala Lake, we find the magnetotactic bacteria. You can go for any lake. So at the bottom in the mud, this bacteria, it is natural gift, the bacteria, and depending on that is specifically the North Pole, South Pole, there's a magnetic, you know that there's a magnetic field from North Pole to South direction, magnetic South Pole, and due to that magnetic field, so the at the bottom you'll find that the migrant. So here we selected that the bacteria from the bottom of the Rankala. So how to collect is very important. It's a natural phenomenon, how to synthesize, biosynthesis, and that's true with the method of microbiosynthesis. Now, as I told you that at the bottom of the Rankala, in the mud, there are some bacteria, they are there. We don't all kind of bacteria, they are there at the bottom in the mud. But then we have to collect the magnetotactic bacteria. So for that purpose, we designed and made. This is our indigenous design. First time we have developed this particular design. You can see that here it is a tube, and here on the both sides there is a magnet. And then he is a magnet, North Pole, South Pole, and then we prepared a tube, and then we dipped into the mud, and then we applied the magnetic field. So when we apply the magnetic field, the bacteria which are only showing the magnetic properties, they are attracting towards this particular here it is. And then we collected the water, and then in the pipette. So the collection of the bacteria from the bottom of the mud, we made a design and of the at different magnetic field, because with the magnetic field, whatever magnetic bacteria only they are collected. So here is the instrument that we have designed collect of this. Now we collected this thing in a pipette or then we put it this magnetic. They have many more but there are some possibility of other bacteria. So what do we do? We took the burette here. Now you can see here North Pole and South Pole. We brought this bacteria collected in the water, and then the concentration of the bacteria in the collected bacteria is very small. So we have to increase because we have to produce the thing. So there must be a large number of antibacteria. So what we did, so there is here is the electromagnet N and S, and then we made a burette. So here you before applying the magnetic field, magnetic bacteria are spread all over the solution. But when you apply the magnetic field at the bottom here, you will see that all the magnetic bacteria, okay, they are attracted here. It means that we are made the concentrated solution of the bacteria. That as collected solution is not that strong in the bacteria, but when you apply the magnetic field, all the bacteria which were there in the upstairs, they're collected here, and so we have made the concentrated bacteria. So this is the basic principle that we brought this law, and then after making the concentration, then here that is a non-magnetic bacteria. Suppose the non-magnetic bacteria N and S. So non-bacteria they spread here. So here magnetic bacteria, so N and S, you can see that they are concentrated here. And then again we are isolated, further isolation, further making the concentration in the lab. This is lab experiment. Earlier was in the field experiment, we collected from the field and then brought in the lab, and then made the electromagnet, attract the electromagnet, and then we concentrate here. So nanomaterial, nanomagnetic biosynthesis nanomaterial. So we produce this thing, and then we cultivated this thing. While cultivation, this we are giving there is schematic here. The schematic experimental representation, that is you can see that A, B, C. And when we apply, put the magnetic field, so there is growth of the magnetic, they are increased. Initially, there were few bacteria, but then you can cultivation of the bacteria in the laboratory, they are there. And then after cultivation of the bacteria with many concentration, okay, applying this thing, so we got, okay, these are the bacteria. Earlier picture, you might have seen that very few magnetism there. But here, in the laboratory, when we treated them, that you will find that, okay, the concentration, very big, strong magnetosomes, they are there, consisting of Fu2O3. That is the magnetic material. And then breaking this, magnetic bacteria, we got this magnetosome, and then we studied their property, magnetic property. You can see that the magnetic property, this is a loop, hysteresis loop, and then we can't characterize these things. So depending on this thing, we characterize the magnetotactic bacteria and for making their decision. Then, what are the advantages? So this is a new method. Available locally bacteria in the Rankala, and then we made the magnetic bacteria rather than physical synthesis or chemical synthesis, microbial synthesis, and then you can see that advantage of microbial synthesis, metal substituted ferrite, it can increase the magnetic hardness of the magnet. So the method prepared, the magnetic material prepared from the chemical physical method, this method has a very strong property. So it can increase the magnetic hardness of the magnetic particle. So this is the nanomedicine. You can prepare the it's the one way of the nanomedicine. Then increasing the coercive field physical properties, narrow size distribution, because it is very essential for the medicine, because broad side distribution, if you prepare the same material from chemical, physical, you get the broad side distribution. But in case of the microbial situation, you get very narrow distribution, highly crystalline, very essential, better shape control, and then mono dispersive, specific size image, because you know that. And then it's very important that suppose I wanted a nanomedicine of 40 nanometer, which has a strong property, which are tested by maybe the lab or maybe the in vivo or in vitro. But then suppose if I want to get 16 nanometer, so it means that we have to prepare, we have to train, we have to develop the magnetic bacteria, which will prepare only part nanometer, which I require. And for that purpose, the size of the control of the magnetism, that will depend very much on what feed you are putting into that petri dish. And accordingly, you can change, monitor or prepare the whatever nanomaterial size that you need for that medicine prepare, and it's a very, very key parameter specifically for nanomedicine to prepare the magnetic nanoparticle. You can see that very strong, sharp. So this is the work I'm presenting. That two of my PhD students worked at Dewa University on application of magnetic bacteria for the cancer, and this there are many other applications I will show you later. But first I'm concentrating here how they prepare synthesis of the nanoparticle nano to make the nanomedicine, and that's a very property. Then whatever nanoparticles we have prepared, then we got specifically the for cancer nanotechnology. Now, when I took the charge of this Dewa University as a Vice Chancellor, my aim, in my first lecture to my management, I gave that I wanted Dewa University a medical shop of the body organs. And in order to make the medical shop of the organ, and then the another is that as per the WHO report, we concentrated, we made a team of science, engineers, and doctors. Specifically, as I told, atherosclerosis, second maximum date is the cancer, and then third, diabetes, all the things. So here we wanted to have specifically the cancer or atherosclerosis. In case of atherosclerosis, heart diseases, our aim was, our target was the operation-less removal of the blockage in the heart. And for operation, it means that without operating, one can remove the blockage, because you know that the artery, when there are blockage in the artery, so that is a heart patient. And in that case, how to remove so the blockage, when you have to remove the blockage, and that focus of our research at University, operation-less removal, develop the technology, nanomedicine, nanotechnology, with which we can make an operation remove the blockage. And for that purpose, the basic principle is operation blockage part. It means that we can prepare the magnetic nanopart. That's what I have to, why I have studied my, because I want to attain that operation-less blockage. So I will need the magnetic material. So that magnetic material we can embed, we can make it as a solution. I will tell you later on how to collide solution. When we make the solution, because it must be injectable, and then injectable solution with the magnetic bacteria, then that magnetic bacteria will go, at the artery where the blockage, they are there. And then, when you apply the external magnetic field, so it will vibrate, and due to vibration magnetic particle, then you can remove the things. So that is the thing. Similarly, cancer. Our target was, that cancer, especially when detected in the first stage, second stage, and third, when it detected in the second stage, you have to go for first, as long as it is a small first stage, one can operate it, remove it. Second stage or third stage, the surgeon cannot give the guarantee of removal of all part. Then we have to go for the chemotherapy and the radiation therapy. And then at the third stage is a very, very painful, because when it spread this thing. So then I will explain you the nanoparticles or the magnetic nanoparticles, which are prepared specifically for two things: operation, remove the blockages, the heart, and then painless curing of the cancer. That same material, when I apply the magnetic field, suppose this thing, and apply the external magnetic field, it also gets heated. And that heat can be used as a part of the operation. So these are the, what are the different cancers? They are the cancer in the human cancer is the male and female. It's altogether different there. I need not go into the detail, because pharma people, they need not be bothered. Only thing just I did the slide. So cancer treatment, as I told you that, so primary stage, it may be surgery, and or maybe then chemotherapy and radiation therapy. These are the treatments, they are there. So then the detection, because it's very difficult to treat the cancer patient at the latter stage. But if it's detected earlier, it's easier and cure the patient. So question is that how to detect. So the first stage, the prevention is better, or the early detection is very important. So for that purpose, we use the physics principle here. That is you can see that bioelectrical impedance spectroscopy. So different types of tissue have different electrical. So the simple physics law, that's Ohm's law. When we apply the electric field or magnetic field, so we have used detection. And here, basic principle is that different types of tissue have different electrical impedance resistance. The electrical impedance could be used as an indicator for the breast cancer detection. I'm talking about now. Similarly, the studies show that significant difference in the conductivity, and then breast tissue, that is a cancerous, has a much lower electrical conductivity. It means that without operating the two breasts, okay, we have developed that device to measure the impedance of the breast cancer, right breast, left breast, and then put on that device on the left and right, and then see that what is the impedance, then we can measure that impedance. So here we have the equipment at DY Patil University, that electrochemically, the impedance meter. It means that when I simply measure the resistance or impedance of the tissue, and specifically in the right breast and left breast. So this is the method that we have developed at the DY Patil University, Kolhapur. And then, so similarly, there's another type of sensor, that is electrochemical sensor, piezoelectric sensor, optical sensor, to detect this thing. And for that purpose, the different sensor, and similarly, the DNA sensor, enzyme sensor, immunosensor, I do not go to this. But all the sensor, this can be making such kind of devices along with the medicine. It is okay. The medical instrument, preparation medical instrument is equally important. And for that purpose, we are again submitted a project, the development of electrochemically, just like the development of magnetic nanoparticle, we have got another project. So this is another project, development of electrochemical immunosensor using functionalized and magnetic nanoparticles for detection of tumor markers. And this is the DST nanoemission funded project, that is total cost that was maybe 89 lakhs 30,000. This was project sanctioned to me in the DY Patil University to work on the specifically functionalized nanoparticle, magnetic nanoparticle. As I give the one example of this thing. So this is, and so this is, you can see that. So these are the objectives of that particular project, that we have completed the project, we have succeeded at the project, we have synthesized the magnetic nanoparticle based on this thing. To synthesize magnetic nanoparticles and their characterization that I explained, fabricate an electrochemical immunosensor based on sensitize the MNP, to characterize electrochemical immunosensor with the CV method, we are using rather than a current voltage method, IV method, we are using capacitance cyclic voltammetry, CV, and then EISMT to optimize the sensitivity of that particular thing. So these are the projects sanctioned by DST to work on this thing. And so this is the structure, how we made it. I need not go with the technology, that how we have made this thing. But this is the new trend to develop the, develop devices, basically curing them. So this is a sensor. And here you can see that the sensors to develop the measure the cancer. So here you can see that the ELISA, PCR, biomarkers. So these are different things. So here, first method, you take the 4 to 5 hours, and then is sensitivity microgram per ml. Similarly, if you go PCR, 4.5 microgram per ml, and here you can see biomarker. So here, electrochemical immunosensor that we have developed with the help of the DSC project, blood fluids, which will use the blood fluid, 2 to 3 hours immediately, very inhuman, rather than 4 5 hours. So here our method can develop within the 2 to 3 hours, and very low. This is very important. Rather than microgram per ml, we can detect very at early. So the early detection of the cancer is very important, and this is nanogram per ml. So microgram per ml, it means that 1,000 times our device is 1,000 times sensitive than the existing device. And so this is this device. So then magnetic, so this is one application we thought that specifically for the cancer. Now, then we attempted the another way, that is magnetohyperthermia therapy, painless, that is, I've just told you, painless curing of the cancer. Without pains, one can create the cancer. This was our target at the DY Patil University. That those, and so here you can see that those who cannot be cured by medicine can be cured by surgery. It means that we have to remove. So this is the statement. Then similarly, those who cannot be cured by surgery can be cured by heat. And those who cannot be cured by heat are probably incurable. So this is the principle, and this is statement Hippocrates, that is 470, the father of the medicine. This is the statement of father, that is, those who cannot be cured by medicine can be cured by surgery. Those who cannot be cured by surgery can be cured by heat, and those who cannot be cured by heat, okay, are probably incurable. So it's very important statement that is made by our earlier, father of medicine, Hippocrates. So here, and then, so here you can see that from the above statement, the heat is very important. So treating the patient, patient with the heat is very important. Especially for the cancer, the painless curing of the cancer. How to treating the painless cure of the cancer. And so for that purpose, we have to make the nanoparticle, which I told you that, which are made from the biosynthesis method, from Rankala tower and all the things. So we have made the solution. And here is the machine where I can make the alternating magnetic field. And due to when I made the alternating magnetic field, the magnetic nanoparticles in the fluid, so they are vibrating and creating the, okay, because we need the injectable magnetic field. And we, after making the injectable magnetic field, so our different materials, for the different properties, then we have to heat this thing. So this is a device with which one can heat the material, and then we have to study the material. I have developed a lab of this hypothermal therapy, this thing, and we have published a good number of papers, the Dalton transaction. Here you can see that this is a paper in the Dalton transaction, so very high impact factor. Induction heating studies of dextran-coated MgFe2O3 nanoparticles for magnetic hypothermia. So this is the one. You see, as I told you initially, I am not just taking from other things, I'm explaining of my work. So here this paper, you can see, VM code, AB Salunke, ND Thorath, and perhaps friends, many of you might be knowing the person, Dr. ND Thorath. Dr. ND Thorath is my PhD. He was my MSc student in Shivaji University. When I joined the D.Y. Patil as a Vice Chancellor, he joined with me for his PhD degree in D.Y. Patil University. And the PhD problem given to him was the cancer. The hyperthermia therapy, developing a nanomedicine, to treat the painless cure of the cancer. And so this is he is one of the authors. Friends regarding Nanthola, after completion of his PhD degree, he got many more, fellowship abroad. And specifically in COVID-19, he was one of the leaders while developing the vaccine, specifically from Pune people and Oxford people. So he was one of the scientists, and then he did a lot of projects. Friends, let me tell you that I'm proud that to be a teacher of Nana Thorat, that because there are, we know that the quality of the person when we measure, FR Fellow of Royal Society in London. Fellow of Royal Society of London is a very important, it's a very prestigious fellowship, prestigious award. This thing. So there are many more FRCS, FRC, Fellow of Royal Society in chemistry, but there are not Fellow of Royal Society in medicine. Dr. Nona Thorat is the only person in India who is the Fellow of Royal Society in medicine. And he is my student, worked in D.Y. Patil University, and he studied his work specifically in the hyperthermia therapy, painless cure of the cancer. Now he's doing a lot of work for this thing. So these are the typical examples. They are there. I need not go for these things here. So these are the property of the materials that were prepared. Specifically, we have different. Now earlier I have explained that Fe2O3, here MgFe2O3, because the property of the magnetic material, strong magnetic field, there must be nanoparticle. It must be strong magnetic because when there is strong magnetic field, so there is less number of particles. You need less than particles. If no magnetic particle, less magnetic property, you need more thing. So then that will affect on the body. So here you can see that that is a MgFe2, the nanoparticle we have studied. So my group, specifically 4-5 groups, they are working on the painless curing the cancer. As I told you that to cure the cancer with the help of hyperthermia therapy, and that we did a lot of work. And so these are the medicines, especially new trends in the pharma must come ahead, and we perhaps that is a new area, and that's I have predicted, basically Viksit Bharat 2047. Yesterday only, I was invited by to Kolhapur, Sanjay Ghoda University. They have organized a big program. More than 2,000 students, they participate in the program, and I was chief guest to inaugurate that science Star Tech activity, Science Star Tech 2025. I was invited as the chief guest, and more than 2,000 people attended. So in Vikasat Bharat 2047, so such kind of activities, students must be made aware of. These are new frontiers, new phenomena. They are there, and so this is the things they are there. So these are the different other technical things they are there. So this is another paper that is AC magnetic field, and this is another. This is my Nikam Jadhav, Khod, Patare, and most of these they are abroad. They are working by virtue of their publications in very high quality journal, and then their applications of these new trends, especially in medicine, new trends in pharma. So these things they are there. So similarly, there are schematic representation of the specific how the hard and characterization of the nanoparticle cell structure and the so then you can see that specific absorption resistance, because when you want to make the optical, specifically in case of the cancer, you know that the cancer say they survive even up to 50 degrees centigrade, but cancer they die down. A normal cell survive up to 50 degrees centigrade, but nor cancer cell do not survive after 40. So if you raise the temperature 42 degrees centigrade, and then automatically the cancer cell die down by the hyper, that I told you, heat, producing the heat within the body, a localized. So there is no effect of on the body. So that's why there won't be the pain. So painless curing of the cancer, it means that when you prepare the magnetic nanoparticle medicine, inject that thing, I mean, then in the tumor, and then apply external alternating magnetic field, which will help to raise the temperature, and then we raise the temperature up to 45 degrees centigrade, and then can cure the patient. So this is a new technology is being coming up, and this technology develop new medicine, it's a new horizon, new area of the farmers. So here you can see that the applied field and then specific solution for different things. So they are there. I need not go into the technical details of this thing. The second application, specifically the drug delivery, is very important. So drug delivery, to make the drug delivery, the nanoparticles which are prepared are scaffold. So it is a passive targeting this thing. So here you can see that the traditional drugs and nano drugs, specifically in case of cancer, in chemotherapy, when you use the drugs, okay, they spread all these things, and there's a large damage, large pains for this thing. But if you consider the nanomagnetic, so it goes, I mean, it doesn't spread anywhere. So you can encapsulate and then target therapy is very important target therapy. So how to release the drug, how to load the drug, how to release the drug, the phenomena is indicated here. The hitting, so it can make the, when you make the magnetic particle hitting, it release the drug. So you can see that is a particle where you have the nanoparticle, magnetic nanoparticle, as well as the medicine. And then you can see that here the hitting. So when you hit it, okay, it will spell, and automatically that is. So after reaching, targeting that, and that targeting can be made with the help of, since it's a magnetic structure. So that magnetic structure, it can carry where you want by using the external liquid. Once you reach there, and then at a time, suppose now release the drug, so you can just reheat it small, and that heat, I know you have told you that vibration magnetic field, so you can release the drug as and when you need it, and whatever quantity you need it, only that quantity can be released. Similarly, another method, that is the magnetic field. So you apply the magnetic field horizontal, so there's a vibration is there, so you can release the drug as and when you want it. So controlled, not only drug delivery, but controlled release of the drug. Loading of the drug is very important. So these are the different things, mechanisms, they are there in case of therapy. And then how the magnetic bacteria, tumor is cured. You can see that here, the different stages where you can, this tumor is broken by just simply putting this thing. So this is the fiber, as I told you, cancer treatment using nanoparticles, the nanoparticles. So the tumor cell with rotating electromagnet. So this way the rotating thing, similarly tumor cell with vibration cell, and then the cell damage with MNP oscillations, and then cell damage after MNP, so rotating this thing. So there are different techniques, they are there. So in medicine is very similarly, we have done some work on DNA nanobiotechnology. In case of DNA nanobiotechnology, you know that at the center we have the in the center, you can have the DNA, is a DNA, and DNA size of the DNA, just look at the size of the DNA, you can see that it's just a 2 nanometer, and for height is maybe the 10 nanometer. So the diameter. So this DNA can use also the sensor. And then how to break the cell, because to make the DNA sensor, you have to collect the cell. Within the cell, you have to break down, and then we can these things. So I need not go into the details there. Now, there's another area in nanomedicine, that is this particular field, that is nanobiotechnology, atherosclerosis, and after doing the cancer. So one group was working on development of magnetic nanoparticles specifically for hyperthermia therapy, painless, the painless curing of the cancer. So another group of my research students, who are 22 PhD students, I have produced in the DY pattern. So another group of students, they were using for the operation less remove the blockage in the heart. And so here that can be done. So that was another group was prepared, specifically the heart. I need not go to this thing. And then, okay, one can find out where are the, these blockages, they are there. So this artery and these blockages, okay, this is standard phenomena. So we have to remove these, this blockage. For these blockages, so whatever I just the medicine we have prepared, that is injectable solution, can be brought it here and then vibrate it here, this thing. Then when doing this vibrating field, perhaps you know that there can be damage. And to make the cure that, so curing is very important. So for that purpose, in DY University, I started MSc in, to start hypothermia therapy, I started MSc in medical physics, so they can study all nanoparticle particles, study their cancers and this thing, therapy. And then another group, they started for here for the atherosclerosis, vibrating thing. So this is another area where my PhD students, they're working. So then there are different terms. There are atherosclerosis, the HDL, this thing. So then atherosclerosis, the nanorobots, nanoelectronics, nanomedicine, unfortunately not work which is being done in India. However, the developed countries like Australia, and so the lot of work is going on the atherosclerosis, the nanoparticles, nanomedicine. So our pharma industries, they must follow this thing. So these are the atherosclerosis, how this can be done, this thing. I need not go this technical report for this thing. So here you can see that the nanorobots. So there are different, so rather than going these things, so these are the things that can be developed here. Then it is very scaffolds, that is injectable scaffold. So for loading the drug and unloading the drug, we have to make the scaffolds. And with the help of scaffolds, so these different scaffolds, they can be made by the electrons come. So we have developed this technology also in the DY University. So these are the one of my PhD students also worked, made these things and studied these properties. So then another area, that is, that the medical organs. As I told at the beginning, when I took the charge of the vice chancellor of the DY University, I made I declared that I wanted to make DY University a medical shop of the body organs. So these are the body organs. It needs to be implanted in the body. So how to make this thing? And to make the implanted body, what is the material is needed to make such a body? So that is help of silk fibroid. Friends, the material is needed to make the body organ, it is silk fibroid. And we have done lot of work, basically at DY University and later on in Siang Institute on the silk fibroid. Recently, last February 2024, we have organized an international conference on silk fibroid and sericulture resources. Prior to that, I have done some work in DY University. We have developed, with the help of silk fibroid, we developed a wound healing material, wound dressing material, and not only dressing material, for dressing one can use the cotton dressing and all things, but we made the wound dressing material, the silk fibroid, with nanobiocomposite, specifically doped with the zinc oxide. And zinc oxide is the property of the light absorption. So when you make the light absorption, it kills, because it develops the electron holes and it kills the bacteria and all the things. So this book is published again, the silk fibroid, Nova Science published America, USA, and that is Shivaji Pawar. So this is the book, and based on this particular book, to make the body organs. So perhaps you get some time, you visit the Divapati University. That, I mean, whatever ideas I started in 2006, now it is coming up slowly. Some body particles, basically in the group of stem cell and regenerative medicine, which I started when I was the vice chancellor, and now it has grown up to such an extent. Now they are fabricating some bioparticles. They are there, and similarly, you can see that using of the this silk fibron, you can make bone, ear, brain, eye, skin. All these particles can be, the body part can be prepared with the silk fibron, for which we will organize the international conference here at to Solapur, the work on this thing. Similarly, there are other drugs, the things they are there for the silk fibroin and the functions of the nanoparticles. So they are there. So similarly, you can see the similar thing, how the body organs can be made with these things there. Then another very important area, specifically similar to the work, there's a lot of things I will not be able to explain in one lecture, because the work which I have done 10 years with 22 PhDs, every PhD student is all new ideas and our indigenous idea. And we have got a lot of papers published. I will not be able to cover. Now, you know that during the last, from 2019 to last recently, COVID was we have suffered, whole world is COVID. And this is the first time in the history of the medicine, any kind of drug existed for a pretty long time. So this is the unique example. The COVID lasted for a long time. Then at that time, I was at the Baramati and working as a research director. In Baramati, we had some collaborative work with the medicine people. As long since I belong to we signed a MOU between the Divapati University Kolhapur, my CRAR, Center for Research, the Baramati, and there was one more Ayurvedic industry. Then we formulated some practically. So in the photo, then at the same time, why there is a spread of this COVID, this thing. So then photocatalytic disinfection of pathogens with TiO2 nanocomposites. I explained how the nanocomposites, that is when a nanoparticle is doped into the that biological particle, it becomes a nanobiocompensatory. And the property of bio-nanocomposites are very altogether different, very strong, very good property we do get with bio-nanocomposite. So in order to control the COVID-19, which was all the spreading and this thing, we did some work, and then photocatalytic, it means that making use of bio-nanocomposite, cell fibron, that is disinfection of pathogens, TiO2 nanoparticle prepared, and control the diseases, this thing. So for that purpose, anti-COVID nanotech mission, I went to this thing. So here, protection of the COVID, that is the protection of the COVID, detection of the COVID-19, inhibition of COVID-19 spread, and post-COVID nanotechnology treatment. So these are the areas which were focused in my. So antimicrobial activity of TiO2 nanoparticle powder based on the surface coating of the. So why is the spread? Because since it is a communicable disease, so it goes from one person to other person, maybe spread with the air and this thing. So we did some work on this thing also. So here you can see that this COVID development of new antiviral. So this is again the development and testing of antiviral selenium nanocoats. This was a project submitted to the Center for Innovative Applied Research, CRAR, Anekantha Society at TC College, Baramati. I did some work on this thing. So this is the COVID lab, established in collaboration with the Divapati University, Divapati Medical Hospital. And the student who worked with me, because of tuberculosis, because it is very difficult. Research students do not dare to work in non-communicable disease because it is very risky. And one has to work in a very, very hard conditions, protecting yourself, and it is very harmful. But fortunately, Dr. Deepak Sawan, who was my student of microbiology, you see, though I am the professor of physics, material science, but become the vice chancellor of Divapati University, and then a student from biotechnology, student from this microbiology student, because this thing, he worked on tuberculosis, and he had the experience on working on the bacteria. So this is the, and then as soon as he finished his PhD, immediately the COVID started, and then Divapati University entrusted the whole responsibility of developing the SARS-CoV-2 lab, testing lab, at the Diva Patel University, and Dr. Deepak Sawant took the responsibility because he had some experience, just a PhD in tuberculosis. I mean, he worked with this thing. So this is the anti-COVID nanoparticle. So inhibition of COVID. So these are the things of the activity. Preparation of the antimicrobial surface coating. So in order to inhibit, stop the spread of COVID. So we developed antimicrobial spread coating nanoparticle. And here you can see that whatever work we did. So here in the paper, 5.4 impact factor, nanoparticle engineered photocatalytic pens, a roadmap to self-sterilizing against the spread of communicable diseases. We took this is very, very interesting work that we did at Baramati. And then, based on that, one of our student, Vijay Mote, and then Milind Tarade. Here, Milind Tarade is the civil engineer. Vijay Mote is again the student of physics here. And then other physics, R.K. Sharma is the dean of the medical college. So with the help of medical. So with the help of engineering, he is a student of engineering. He's a student of physical sciences. He's a dean of the medical sciences. And I myself, okay, the expert in nanomedicine, nanomaterials, that what I have done this. And this particular research paper, catalysis, with 5.4 impact factor, when it was published, it was a very interesting reaction or report, just like when I gave the first lecture and after inaugural function in the ATAL FDP program, I understood from the organizer that, oh, there was very good response from the those who attended conference and good response. So similarly, when we publish this particular paper, and based on this particular paper, here is the remark. You can see that he's the edit, that is Dr. Bray from the UK. She has remarked that one of my colleagues, after publishing a paper, one of my colleagues draw my attention to a research paper entitled, that is exactly whatever I shown it, and my online reading of this paper came to be the discovery of the new realm. Friends, it is a very, because she is the editor of many group of medicine journals. And when it went through our paper, so she said that she meant that this is a new type of innovation. And then she referred all these things. And then she offered me to be one of the part of their editorial team and all this. So this is the work that we are the important of the work and how we made. That is the paper published. Then how we made, because a civil body. And this particular one, because when the patient are there, so when suppose specifically this work has done for the tuberculosis, because in a hotel, suppose somebody stayed earlier who is a patient of the this tuberculosis patient. So whole night, okay, all the coughing, and then the bacteria, they may absorb surface. And when next person comes next day, so he will be affected. So in order to avoid this thing, we wanted to develop the pen, civil engineering. So this man is civil engineering, physics people, photocatalytic people, and then prepare that tape along with the this thing. So then we found that this is pen, and then bisectoring of this. And then at the same time, in the Baramati, in the Ayurveda, we had a collaboration with one of the Ayurvedic industry, my research center, and the Diva Patel University, dean of the medical faculty. We developed the drug, specifically nasal oil drops, and that was due to the Artemisia pallidum, Davna. So from Davna is a, and then we made a first zinc oxide bus, and then the mixture biocomposite of Davna, Jasad bus, and then some oil media. So we cured Baramati rural hospital more than 1,500 patients based on that bio nanocomposite muscle drug. And based on that, I have done a lot of work specifically in the medicinal plant and then how the medicine. So during that particular period, the patients treated with the Ayurveda, maybe not this thing, it takes long time, but there is no after effect. The patient treated with the allopathic pain, okay, there are not many problems, they are there. So there's a third line of the, because still Ayurveda medicine, especially foreigners, they do not depend much, they do not appreciate because it takes a long time, this thing. So that's why, so we have developed here rather than Ayurveda with nanomedicine. So So nanotechnology applications in medicine, nanotechnology application is medicinal plant. And so you can find that here, I have this again, I'm very happy that just recently, a few months before, nanotechnology application in medicinal plants and their bio-nanocomposites, the Ayurvedic approach edited by Shivaji H. Pawar. This is another third book on the places in medicine. Specifically, these are very, very important, specifically in the frontier area of pharma. So what should be the new trend at present is not the trend, but maybe after a few years, these pharma people must have the large thing, and based on this thing, we have made the development of photocatalytic Ayurveda Jasad Basma, which I just told. This was the proposal, Professor Mittal to Biotechnology. Similarly, another photocurable silk fibroin based on tissue sealants. So we work on that again with the help of silk fibroin and make the tissue. It means that henceforth, if you develop this thing, we need not have the sutures. So there is one can make just a gum, silk fiber and gum, and then after opening for closing that wound, you can make use of this gum that can be prepared another area. Similarly, innovation is a bio-nanocomposite drug derived from the bio-nanofortification medicinal plant for virology application. Because for COVID-19, so we have again another area where this some of my work has been done. Development of the photocatalytic Ayurvedic jasad, which I just told you, jasad bus for this thing. And similarly, the photocurable silk fibroin based tissue sealant that I just told you. These are some of the papers elsewhere, and that is preparation. Specifically, we have concentrated on specifically very important for the pharma people how to prepare. And as I told you that the key parameter for the pharma nanomedicine is that controlling the size of the nanoparticle is very important. This should not be broad range of the size because as the size changes, there is a change in the property, tremendous change in property. So for pharma research, so these are another paper, synthesis and characterization of chitosan TiO2, some development and photocurable antibacterial activity, the nanoscience are there. So this thing, structural tree refinement and photocatalytic activity, if you dope, so all these papers, Deleker and all this Hemraj Yadav and all this is my group working. So we have done a lot of work in this area. Visible light, photo induced. This is another paper elsewhere paper. Then this is you can see that another paper here. There is surface coated building studies healthcare. So this is an area similarly antimicrobial activity of TiO2 this thing, and this is specifically in order to go ahead. So we wanted to have, our country wanted to have the collaboration with Russia, because though we are working, so now it is the era of collaboration. It is not the era of working in isolation. So for that purpose, government has made a committee to visit Russia. And here you can see that Dr. Professor, under the chairmanship of Vijay Bhatkar, I myself was one of the members of this. We visited Russia and then studied furthermore the applications of nanotechnology in the medicine and with the collaboration with the Russian people. This is one area. So this is, you can see here the picture. He is a Nobel laureate because you can see that in order to make the nanomedicine and this thing. So he's a professor. Then I myself was there. And then at Tiruchanagadi, I was invited as a Nobel Prize. That is Ivor Giavier. He has synthesized, brain tumor, how to make the brain tumor, the Josephson junction. He is the father of Josephson junction to detect rather than opening the head, one can detect the thing that is without. So the device which made based on a superhightis and superconductor, and he's the father. This particular teacher engineering college, they organized all top 100 and 100% out of 100 students, 600 were selected, and they invited Nobel laureate to open this. And India, and this college wanted, they let there be somebody else from India to share the dais with the Nobel laureate who has worked on such kind of area. Fortunately, I was very fortunate to be on the dais of this particular area. So this is the thing, you can see that. And then this is my group at Diapat University, 12, 14 different universities I started, because the first term I make the Diapat University, in the history of the, university, getting A grade to the college is the first exam. That's why I got another second term. And in second term, I make that college university as the top 100 university in the world. These are my actually what your work have discussed. So here is my PhD students at DY Patil University, and they have tremendous, fantastic work, specifically in pharma, new trades in pharma. Exactly every research work can be a new industry, and it can be future maybe another 25. So this is I'm very lucky to have very such kind of galaxy of students to work specifically in the field of nanomedicine. And this is thank you very much for your patient listening.
Thank you very much, sir, for sharing such valuable insights on the topic. Now we open the floor for question and answer session from our participants. So I request all the participants, if you have questions, you can simply unmute yourself and please ask the questions, or you can put your question in chat box too. Yes, any questions are there?
Good evening, sir.
Good evening.
This is Dr. Panchashila.
Oh, yes, ma'am. Thank you.
Sir, this is really a nice work, and I really would like to tell audience that yesterday sir was there in Sanjay Godawat, and he has traveled around 300 kilometers right now. And immediately he started his lecture. So I really appreciate his energy and the dedication towards research. So I have one question, sir.
Please, madam.
You have gone for extraction of the magnetic bacteria, nanobacteria from the Rankala Lake. So how you check the biocompatibility of that bacteria?
We have made some experiments on biocompatible with the help of Pune people. We don't have that facility with us, but we have tested it biocompatible. We can check it. Because cytotoxic effects and all the things that we don't have that setup. Now the DY Patil University, now they have developed this, but at that time we didn't have that. So my student took the help of some, because some of students, they are abroad. So there we have a good linkages between our students and the students who my students gone abroad. So with the help of those people, we have tested this.
Okay, sir. Thank you so much.
Okay, thank you.
Hello.
Hello.
Hi, am I audible?
Yes, ma'am.
This is Suvarna Kshirsagar from Sinhagad College, Solapur.
Hi, yes, madam, please.
Very good session. Yes, sir. Very good session. I have one question.
Please, madam.
Yes, sir. Like magnetic nanoparticles, can we use silk fibroin for drug delivery for any type of disease?
Is a very good question. Silk fibroin is a biocompatible, non-cytotoxic effects, and it is a very strong thing. One can make use of silk fibroin scaffolds, and then in that scaffold, one can incorporate the magnetic nanoparticle. So that or the device or medicine inside that. And in order to release this, one can make the silk fibroin material with the magnetic particle dope. So it's a good question, and this can be a good topic even for the pharma, develop the new material, magnetic material. And then since if you dope this silk fibroin with TiO2, it becomes it can be magnetic. So to release and load the drug, so that will be possible with this thing. At present, for in drug delivery, silk fibroin material is used as a scaffolds for embedding the drugs and all the things. Thank you, madam. This is very
Thank you, sir. Thank you.
Okay.
Hello.
Okay, so
Hello.
yes,
Hello.
anybody?
Hello.
Hello.
Hello. Can you hear me, sir?
Yeah, please. Yeah.
Sir, the session was nice.
Oh, thank you very much.
Sir, is there any bacteria? Hello. Sir, is there any bacteria which can improve the soil properties, the strength properties? As an engineer, I'm talking about.
Of course, I'm not the person from, I have not much done work on this, agriculture, work, soil and all the things. But certainly it will
It's
help.
not
Now,
agriculture.
yeah,
Sir.
you are right.
Talking about
Nowadays, there are some program, one drop optimum crop. And in that case, in order to, in addition to the fertilizer, so, water holding capacity is very important also there. And maybe with the help of some of this biological work, it may help to, increase the water holding capacity. And then it will be with the sensor, like with the sensor.
capacity will increase the agricultural yield and all. But as far as the structures are concerned, it should not hold the water. If it holds the water, no, the strength properties will come down for us.
Yeah. Perhaps I don't have much experience in that area. So maybe it's a good topic. Certainly, if you can discuss.
Yeah, I'll collaborate with you, sir. Then in that
Sure,
case.
it's my pleasure, sir. Because this is a new area, but I'm really ready to work with the whatever little knowledge I have and your knowledge. Perhaps we can come together and do even research in that area also.
Okay, sir. Okay, sir. Thank you very much.
Yeah, if any questions are there, please. Okay.
There is
So I think,
one question
Good
in
evening,
chat
sir.
box.
Good evening.
Good evening.
yes, sir.
It's
There is a question in chat
Makanda
box.
from Dixie College.
Oh, yes.
I just have one question, sir.
Please.
I just wanted to ask about a nanoparticle that is titanium oxide. Can we have a substitute for that particular
You see,
with the same properties?
specifically, we have used TiO2 nanoparticle for its high photoactivity property. It means that suppose there's a light is incident on that, so it produces electron holes, and these electron holes, they are we can produce reduced species, oxidized species, increase the reduced species, oxidized species. Even it will the photo irradiation will help to maybe increase the property of the nanomedicine. Specifically, as I gave the one example of the nanomedicine nasal oil drops. The nasal oil drops were prepared. Jasad basma is nothing but it is zinc oxide basma. And zinc oxide basma with the help of, that is artemisium involved. So in order to increase its effect of light, when due to the TiO2, suppose if we irradiate TiO2, it produces the reduced phase oxidation species, and that kills. It means that we will improve the strength of the medicine. And when you increase the strength of the medicine by irradiation, then you need very small dose of the medicine. You can reduce the dose of the medicine. And so with the photocatalytic induction, increase the property of the medicine is possible, sir. Yes, sir.
Okay.
And for replacing the TiO2, there are so many zinc oxide, so many bicompatible oxides, they are there. So this can be replaced later. Only thing by TiO2 is large band of energy. So we can try for another, but we have not done this.
Okay. Can that be used in the fuels also, sir? Will that yield the same properties? To reduce the emissions or something like that in the field of engineering?
Okay. Specifically silk fiber, perhaps I do not know whether you have heard my first lecture or not. There are specifically energy conversion devices, generator, or tribolic nano generator, piezoelectric nano generator, and specifically even smart clothings that silk fibroin can be used, even protection from the viruses. The silk fibroin has lot many properties, and that can be used for these things.
Okay, thank you very much, sir.
Thank you, Ajay.
Yes, friends. Any questions are there? Please, you can ask. Okay, so I think there are no more questions. So
Thank you very
it's
much.
time for a vote of thanks. So on behalf of organizing committee, I extend my gratitude to Dr. S.H. Pawar sir for his insightful session. So sir, your knowledge and experience have provided us with deeper understanding of the pharma industry's evolving trend. So thank you, sir.
Thank you.
So friends, now it's time for a short break. So It will be for 3 or 4 minutes, and after that we will resume again. Okay.
Taban sir,
Yes, ma'am.
next speaker has been joined, Debanjan, Dr. Debanjan. You just make him co-host.
Yes, ma'am. Yes. Jokare sir.
Yes, sir.
Jokare? Yes. So
I will make him as a co-host
yes, yes.
in a minute.
Yes. Yes.
Savansan.
Yes, ma'am. So
Can
shall
we
we
start?
start second session?
Yes.
Yes, yes. Okay. So friends, now moving on to our second session of the day and overall session number 8. The topic of this session is large scale synthesis and shaping of metal organic frameworks and application in selective CO2 capture by Dr. Debanjan Chakravarti. And it's my pleasure to introduce Dr. Debanjan Chakravarti, a distinguished researcher in the field of porous materials and gas separation technologies. So Dr. Debanjan Chakravarti completed his PhD in inorganic chemistry from prestigious Indian Institute of Science, Education and Research, that is ISER Pune, in 2020 under the guidance of Professor Ramnathan Vaidyanath. During his PhD, he specialized in the synthesis and characterization of various porous materials such as metal organic frameworks, covalent organic frameworks, porous polymers, and hydrogen bounded porous frameworks, all with applications in gas separation and catalysis. Following his PhD, he joined the renowned Institute of Porous Materials at Paris as a postdoctoral researcher. Currently, he is working on a collaborative project between IM, AP, and Total Energies, focusing on the large-scale synthesis and shaping of MOFs for selective CO2 capture, a critical area in sustainable energy solutions. His research contributions have been widely recognized in international journals and even led to a patent reflecting the impact of his work in this specialized domain. With expertise in advanced material characterization techniques, gas absorption studies, and large-scale synthesis methodologies, Dr. Debanjan Chakravarti brings invaluable insights in fields of energy-related applications of porous materials. Also, Dr. Debanjan Chakravarti has extensive expertise in cutting-edge analytical tools and techniques. Some of his core technical skills include X-ray diffraction techniques, including single crystal and powder XRD, thermal analysis through thermogravimetric analyzer and related systems, microscopic tools, including FESEM, AFM, and TEM for material characterization at the micro and nanoscale. Expertise in computational techniques like material studio and Gaussian analysis for simulation and modeling of chemical systems. Mastery in scale-up techniques such as large-scale reactors, autoclaves, and spray dryers, as well as shaping techniques like extrusion, spironization, and well granulation. So we are truly honored, sir, to have you with us today. So I request Dr. Debanjan Chakravarti, sir, to deliver his session. So over to you, sir.
Yeah. Am I audible properly?
Yes, sir. Yes, sir.
Okay. Thank you for the kind introduction. And I think I am the youngest in this session. Like before me, the distinguished professor has spoken about his research. And so do I need to share my slides or you will do it?
You can share, sir, from your end.
Okay. So just a
You are
minute.
now host.
So I start sharing my slides. It's good. So it's seeable, right?
Yes, sir. Now it is visible. Just you can make it full screen.
Yeah, I'm making it full screen. So it's fine now?
Yes, sir.
Okay. So hello everyone. Good evening. So I'm joining from Paris now, and it's midday here, but still I say good evening to all of you. So the topic of my research throughout my PhD is porous materials. And when I moved to Paris, I started working in metal organic frameworks. So I'll discuss what is metal organic frameworks and how it is a related application for CO2 capture. But before I go into my topic in details, let me introduce what is CO2 capture and why it is so emerging field in the world. So since I'm very young, I can tell you that now in Europe and US and these Western countries, CO2 capture is a main research area where the different companies, different agencies are investing their fundings. They are investing billions of euros and dollars to do this because they want to make it net zero carbon by 2040. So in European Union, they have one project is called Horizon 2040. So they have made a target that we have to decrease the amount of CO2 emitted from different sources so that we can make a net zero system or net zero environment. So it's very challenging and it's very, very good. So right now I'm working with the academy and industry both. So I'm working in an interface. So I can tell you that how the industry works and how it collaborates with academia so that you can have an idea about how to transform a research from academic level to a industrial level. Okay. And for CO2 capture, what is CO2 capture? First of all, for people who doesn't know about much about CO2 capture, I can say that when you go to some power plant or some cement factories, you see a chimney which is emitting some white fumes out of the chimney. What are the white fumes? These white fumes are practically flue gases. And this flue gas has different compositions, like it has nitrogen, mostly nitrogen, some of oxygen, carbon dioxide, then some toxic gases like hydrogen sulfide, sulfur dioxide, nitrogen dioxide, some water vapor. This kind of components are there in this flue gas. Now, if we start emitting this kind of gases every day, our environment will be contaminated with this kind of toxic gases. And you know, it's very intriguing that in Europe and in US, now the electricity is produced via nuclear fuel. So if the radioactive CO2 is emitted from the nuclear power plant, then it will contaminate our environment and it will definitely cause some problem in our daily life. We'll get different diseases. So it's very important to capture these toxic gases, particularly CO2, before the stream is emitted from the chimney, from the line. So there are different technologies for CO2 capture. And if I name them, there are some technical names like pre-combustion CO2 capture, like post-combustion CO2 capture, like direct air capture, this kind of. And all of these captures have different meaning, and they depend on the concentration of CO2 in the flue gas or the emitted stream. Okay. So today I'm gonna talk about how we can transform academic research to an industrial research by successful collaborations between academia and industry, and from publications to patent, how we can have some economic development also. Coming to metal organic frameworks, So you can understand the name, it has metal, it has organic part. So how the metal and organic part is linked together. So from basic inorganic chemistry, you know that metal can bind to organic linker through coordination bond. So the scientists in 1990s, used this phenomena of this coordination bond to make a polymer which consists of metal and organic part. So when they made this polymer, they called it as coordination polymer. And when these coordination polymers are made into a porous structure, they call it metal organic framework. So in principle, metal organic frameworks are coordination polymers, but they are porous. And what does it mean? Why it is porous? So for students, for very normal person who just started their science, they can understand that a sponge, it can absorb some water when you clean your floor. So it's like that. So it has porous structure. It can absorb different molecules, different gases, liquids, different compounds, and it can store and it can release when needed. So this is the beauty of these synthetic materials. And we can synthesize these materials in our lab very easily with very cheap materials. So which I'm going to discuss that how we are functioning and how we are delivering the metal organic frameworks to the industries, particularly with Total Energy where I work, like in which project I work in the interface. So Total Energy is a very renowned company in France and in Europe, and which provides electricity mainly. But it has different R&Ds, it has different gas absorption sites, it has different catalytic R&Ds. And one of the R&Ds are focused for CO2 capture, selective CO2 capture. And our lab in Paris has collaborated with this company to have a nice system which can be a pilot, which can be transformed to pilot scale, and in future to a proper material which can be used in the industries. So I go to my next slide to describe you what is metal organic frameworks in details. So as I told you, metal organic frameworks are built between the coordination bond of carboxylate linkers and this metal or metal clusters. So so let me just take a pointer. Yeah. So this is the metal cluster and this is the carboxylate on our different azolate linkers. So a thumb rule, when you want to make some coordination bond between metal and linker, you have to follow hard, soft, acid, base principle. Hard, soft, acid, base principle is nothing but hard acid likes hard base, soft acid likes soft base. So this principle we follow to choose which metal and which linker has to be used for preparing a metal organic framework. For example, if you have high charge metal like aluminium 3+, iron 3+, zirconium 4+, or titanium 4+, then we have to take a linker which has hard base like carboxylate. In carboxylate, the donor atom is oxygen, which is hard. So it will form a stable coordination bond. But when you want to prepare metal organic frameworks with +2 softer metals like copper 2+, zinc 2+, iron 2+, nickel 2+, then you have to use a softer linker or ligand like azolates. Azolates has nitrogen donor. So this nitrogen is softer, which can bind to the 2+ metal and give very stable MOF. But if you mix match, like if you want to make a MOF with high charge metal ion to azolate or nitrogen donor linker, you might end up with very less stable metal organic frameworks because coordination bonds are very susceptible to hydrolysis. So this kind of less stable frameworks might hydrolyze in presence of water. So if I recall you that when the emitted CO2 stream, emitted flue gas stream has water, like humidity or water vapor, it can dissolve or it can hydrolyze the bond between metal and the linker. So we have to choose a MOF which is very stable in humidity in presence of water, and the metal and the ligand bond doesn't hydrolyze in that particular condition. So coming to the structure, so here are some depicted MOF structure you can see, and where you can see that it has nice porous channels, porous framework. So you can see the blue ones, inorganic building units like ion, oxocluster, chain, and etc. And the gray one is organic building unit. So when it is forming MOF, you can see that it has nice porous structure and there is a dummy atom inside. And there you can see that atom nicely fits inside the pore. Now we can tune the size of the pore. Like we can use extended linkers, we can use ditopic linkers, we can use tritopic linkers, and depending on the different functionality and different size of the linkers, we can tune the pore. And this tuning is very important because different gases have different kinetic diameters. So if you want to fit CO2, you have to use a particular pore window. If you want to fit water, you have to use particular pore window. If you want to fit some other gases like xenon, like krypton, this kind of gases, even methane, even hydrocarbons, you have to use different pore window. So thus, depending on the linker and the metal constituents, we can change the pore window, pore structure, and even the architecture of the pore of a MOF. So it is very tunable. It is chemically tunable. So we can have different number of metal organic frameworks. And so in subsequent slides, I'll discuss how we have developed metal organic frameworks and how it has been utilized for CO2 capture. So, this permutation combination can give you hundred thousands of metal organic frameworks, but we have chosen the best ones in the world. So going to my next slide, but it didn't change. Why? Sorry for that. Just a second, I think it has some bug. Why it's not working? So I'll restart the sharing again. Okay, so it's working again. Sorry for the disturbance. So, okay, now this is important that we should have very ordered porous structure. And this ordered porosity comes from as I told you, the choice of different metal and linkers. So in this case, you can see we can tune the pore by functionalizing the linkers. Say, for example, in this left side, if I show you, in here, you can see this is normal benzene dicarboxylic acid, 1,4-dicarboxylic acid. Now, if I introduce some functionality here, say, for example, some amino groups, some nitro groups, or some other functionalities, substitution, then it can give a new MOF with a new functionality which can interact with the guest. So we have this kind of important phenomena which we can always tune the pore structure of the MOF. Another important thing is that we can define the MOF with some chemical and structural features. For example, we can have open metal site. This open metal site is nothing but you have unsaturated coordination in the MOF. So when there is one coordination of the metal is not coordinated, that is called open metal site. So in this metal cluster, you can see that when you add water, the water goes and coordinates to the open metal site. And when you remove water, it goes back to the original structure. So through this mechanism, you can have reversible water coordination and decoordination. That means you can have water adsorption and desorption. So this kind of phenomena can be observed in MOF. Another important thing is the chemical and geometrical tuning. What does it mean? It has different effects like confinement. What is confinement? So when you tune the pore size, you can tune the window of the pore. So if you make a very small window, it can create some confinement effect for particular guests. So it's like a sieving. So when you make tea, when you sieve the tea tea particles are not going through the sieve, but the liquid tea is going to your cup. It's exactly same when you can confine a certain gas. So when you pass a gas mixture through a MOF, certain gases are confined into the pore and other gases goes through. This is in reality called molecular sieving. Another important part is the interaction, how the guests interact with the MOF, hydrophobicity and philicity. Depending on this functionality, you can tune the hydrophobic and hydrophilic nature of the pore. You can tune the size of the pore like micropore, mesopore, and you can always introduce some channel or cage-like structure into the MOF. So you can see MOFs are highly tunable, and one of the best materials nowadays is being explored in the world. Another important phenomena is flexibility. So when you stimulate the MOF with external guests like pressure, temperature, some solvent, it can breathe. What does it mean? It can change its pore size. It can be large pore, it can be in very small pore. You can see here, this is in large pore, the pore size is larger, but when you externally stimulate it, it goes to narrow pore. So this kind of phenomena is called breathing. So you can utilize this kind of stuff for different mob development. Now coming to CO2 capture. So CO2 capture is very important, and for that we have a project called MOF4AIR, and it means Metal Organic Framework for Carbon Dioxide Adsorption Process in Power Production and Energy Intensive Industries. This MOF4AIR project just ended last year, and so we have what we have delivered today. I'm gonna talk about that. So decarbonization process of industries. So you can see in this left side that when the coal is burned, it produces different compositions of gases. This composition of gases contains CO2, and this CO2 can be captured by this MOF. And this MOF later, it can used for carbon utilization and as well as geological CO2 storage. So there are two paths to utilize this CO2. Either you store in geological storage or you utilize this carbon to prepare some value-added product like different chemicals. You can do some catalysis to make different value-added products, different fuel like methanol, ethanol, even methane, different things. You can utilize this CO2. This is what the goal of current industries in European Union and in US. My research is focused on this part where the MOF is developed and utilized in larger scale. So to develop and promote the use of MOFs for CO2 capture in energy and industrial sectors, so we have different stages of the research. First, we have to validate the most promising MOFs for CO2 capture. So we have different parameters and to choose which MOF can be used for this process. Then we can fine-tune the adsorption process for the high performance MOFs. And then we can demonstrate these processes for practical operating condition with the collaboration of the industries. So in this kind of different stages, the MOF4AIR project has been demonstrated. And to tell you that this MOF4AIR project had 14 partners. Out of these 14, 4 partners were industries, and these industries belong to Total Energies, Tubrush from Turkey, TCM from Norway, and another industry from France. So these industries have tested the CO2 capture ability of our MOFs in different pilot plants in different parts of the world. So it's very exciting, and when I'll talk more about this, you will find that how academic research has been transformed to an industrial research. So CO2 capture. So as I'm telling, it's not that there is nothing to capture CO2 in the industries. There is a material which can capture in industries, like it is called amine solution. So it's a liquid which has amine in it, and that amine, the NH2 groups, reacts with CO2 and forms different chemicals like carbamates, like different chemicals, and thus the CO2 is captured. And once the CO2 is captured, we take the amine out and we regenerate the amine by heating the amine solution so that the CO2 gets rid of from the amine solution. But handling this amine solution is very tricky because it has different problems. What are the problems? So in this graph, you can see that there are different points, and in these points, point B, point E, and point F, these 3 points are missing in amine solutions. What are these? As I told, the ease of regeneration. So any adsorption material, you have to use multiple times. So you have to use once, then regenerate the material, and then bring it back to work again. So when you regenerate, how do you regenerate? Regeneration is done by heating. And the heating, because you are making a chemical bond between amine and the CO2, this heating costs most of the money invested for the CO2 capture plant. So this is very important phenomena, and I will talk in later slides how we have managed this regeneration problem. Another important thing is environmental friendliness. So when you use something in a large quantity, it has to be very environmentally friendly. It should not be toxic. It should not be volatile. So amine solution is not like that. There are some amines which are toxic, which can polymerize, which volatiles. So this is the problem when you use liquid scrubber. And stability. Why amine solutions are less stable? Because it can polymerize over different cycles of usage. And with heat, when you regenerate, you heat, and in presence of heat, it might polymerize, making it inefficient for CO2 capture in the subsequent cycles. So these are the main problem which nowadays the industries are looking for an alternative adsorbent for CO2 capture or any kind of gas capture. So when we look into porous sorbents, we find different porous sorbents like activated carbons, like zeolites, like organic frameworks, and like porous silicas. So activated carbons are widely used in different sectors like battery industries, like electrical industries, like gas capture industries and all. But activated carbon has different problem for gas capture. Because when you capture a gas, the target gas should be selectively captured by the material. So when I select CO2, our material should capture CO2 in presence of other gases in the mixture. But carbons are not selective to CO2. They always capture others as well. So when it captures others gases, then the efficiency of carbon capture technique decreases. So activated carbons are not good material for CO2 capture. Comes to zeolite. Zeolite, if you don't know zeolite, what is zeolite is? Zeolite is nothing but inorganic compounds which has alumina, silica, aminosilicates, and different metals, this kind of stuff. So zeolites, the problem of zeolites is that they are very much hydrophilic. So think, when in the flue gas mixture, you have CO2, you have water. So when you use zeolite, it will capture CO2 and water both. So it's not very good. And water and CO2 always compete in the capture process. So if you don't capture all the CO2s, rather you capture some of the water, it is not efficient. Okay. Coming to porous organic frameworks and silicas, they are also not very stable, and they don't have good selectivity for CO2 capture. So over the years, scientists in porous materials have experimented, and they came to a conclusion that metal organic frameworks are very good for physisorption based carbon capture. And the regeneration problem can be overcome because it is a physisorption. The gas, the CO2 doesn't make a chemical bond with the material. So you can regenerate the material by only vacuum or flowing some gas into the material. So MOFs can be good candidates, but we have to validate. So what are the MOFs? They are very ordered porous. What are the advantages? Because they are highly tunable. I have already discussed in my previous slides. So when I say that how to choose a MOF, we have to think about these things like sustainability, performance, processability, and cost. Sustainability, if I say what is sustainability, that what are the things we are using, upscaling accessibility, and when we upscale it, it should not affect our environment. So when we upscale, we always do life cycle assessment. We do techno-economic analysis so that to understand that how economic upscaling is and how after upscaling the side products are harming the environment. I will discuss in details. Performance, like what is the uptake, how is the selectivity, influence of impurity, regeneration, and stability. Processability is how you process. So when you want to use something in the industries, in a power plant, in the chimney, you cannot use powder. If you use powder, because of high flow, high pressure drop, your powder will fly and it will clog the entry and exit of the gas. So you will have an accident. So what you have to use, you have to process the material to beads, to some coatings, to some membranes. So processability also a very important phenomena for CO2 capture and for MOFs. Finally, cost. Cost is what are the things you are using, how long you are doing the reaction, how long does it take to filter off the powder, how long does it take to dry the powder, how long does it take to process the powder, the cost of the chemicals, the cost of the byproduct, how we dump the byproduct, what are the effect on environment, space-time yield, and then it comes the techno-economic analysis, finally life cycle assessment. So all of these steps we have to do to make a material, to make it for industry from academia. So it's not a very easy part. Like we in the academic journal, we say, okay, I have got this material, it's very good, it can do this, it can do that, but you can see the real path of the material from going from academy to industry. So the previous speaker said about pharma industries, he also can admit that a material which has been synthesized in lab takes a long time to be a medicine, a practical medicine in the market. Exactly same is happening for inorganic industries, for material industries. Okay. So I come to the first example of MOF which has been commercialized. So this is called CALF20. And I am very happy to announce that this MOF was first synthesized by my PhD supervisor in IISER Pune when he was a postdoc in Canada. So it is synthesized in Canada, and this MOF is very simple. What it has zinc, it has oxalic acid, and it has 1,2,4-triazole. So you make these three components, the linkers, coordinates to the zinc, and makes this kind of porous framework. This framework, you can see it has nice pores. These pores are utilized to have CO2 inside it. Okay. What are the main advantages of this MOF? This MOF has stability in steam, it is microporous, and it has very high CO2 capacity. So CO2 capacity, you can see it is an isotherm. Who doesn't know isotherm? Isotherm is measuring the uptake of the gas or a gas molecule in function of pressure. So x-axis is the pressure axis and y-axis is the amount of the CO2 captured in millimole per gram. Now, when we increase the pressure, the capture increases. Okay. So you can see CALF20 can capture CO2 at different temperatures. These are the isotherms, and you see the red one with the isotherm is at 303 Kelvin, 30 degrees Celsius, and you can see at very low pressure, this material can absorb high amount of CO2 and then it saturates. Then with high pressure, it doesn't absorb any CO2, it is saturating. So our interest in this small pressure region, in this low pressure region, because as I have told you, in flue gas, you have 85% of nitrogen and rest is others along with CO2. So you will have less than 15% of CO2 in flue gas. That 15%, that partial pressure corresponding to this area of CO2. So this is very important to have a low pressure uptake of CO2. And when it comes for water adsorption, you can see there is the water adsorption of CALF20. It doesn't absorb water till some relative humidity. Till here, it is not in absorbing any CO2, any water. But as I told zeolite, it is very hydrophilic. It is absorbing high amount of water in presence of water vapor. So when in a flue gas you have water vapor and CO2, both are competing. So your material should absorb only CO2, not water. So CALF20, which is very good material, is absorbing absorbing CO2, not water, whereas zeolite is absorbing water, not CO2 at that particular working condition. So, you know then after discovery of this MOF in around 2020 or something, then they collaborated with BASF, the chemical manufacturing company in Germany, to make this MOF in ton scale. So they optimized the process in ton scale, and then Savante, the company which is based in Canada now, which is a French company, this Savante started making a pilot plant with this MOF to capture CO2. So if I show you some of the technologies how they capture CO2, so you can see the flue gas, it has nitrogen and CO2, goes in, and in position 2 you have CO2 absorbing material, the calp 20, which has been fabricated as a membrane. It absorbs CO2, and then you have pure nitrogen coming out of 6. Okay. And this is a rotary adsorption machine. This platform rotates, and when you have stream of water, what it does when it rotates is filters all the CO2, and the CO2 comes off as a pure CO2 plus steam. So you have cleaned the flue gas in presence of this MOF. So this is how Savante is now capturing CO2 in a thermal power plant in Canada, in British Columbia. So this is very important that you can see this MOF synthesized in a lab, transformed to an industry for ton scale production and CO2 capture process in an energy intensive industry. This CO2 they are using to convert this CO2 in methanol to use it for some other reason that I don't know exactly, but this CO2 has been utilized. So not only you can capture CO2, you can utilize the CO2 as well. Now, what we did. So this is an example I have given that MOF has been transformed to industries, but what we have done in our laboratory. So in this project, we selected different MOFs. So the first selected MOF is MIL 160. This MIL is coming from Materials Institute of Lavoisier. This institute was established by pioneer MOF chemist Gerard Ferré in Versailles. So he introduced these MOFs, and then my supervisor Christian Serre, he was a former student of Gerard Ferré, who established our lab IMAP. He transformed this MOF to industries. So this is MOF called MIL 160. It has furan dicarboxylic acid, very cheap. This can be obtained from biomass conversion, from bioplastics. This can be obtained in large scale. And there is a company in France, Sintef, who is making this linker in large scale from bioplastics. Okay, so this is very important that you choose your material which are available from bio sources so that you can defend your life cycle assessment. So when this MOF is reacted with aluminium precursor, it forms this kind of aluminium carboxylate octahedral chain, where you can see it is linked through the carboxylate groups here and some hydroxyl groups as well in the coordination. And when it is visualized in 3D, you can see it has nice pores. The diameter is 6 angstrom. The surface area of this MOF is 1220, very high surface area, micropore. And when we calculated that how much does it take to synthesize this MOF in green and in large scale, green means in presence of water. So we make this MOF in water, in room temperature. Normally MOFs are made in high pressure and high temperature reactors in autoclaves, but our MOFs, we always try to optimize them in green and very simple methods. So in green and scalable synthesis, we calculated the production of this MOF. It can be produced in kilogram for less than 30 US dollar. Okay, considering the raw material costs, capital fixed investment, and production costs. So we calculated in different programs, and we found that we can prepare this MOF in a very cheap manner. Okay, so this is very important. And then in our lab, we have synthesized the MOF in kilogram scale. So this is a bucket containing half a kilo of the MOF, and we converted this MOF in our lab to this kind of beads. So in chemical lab, you see the molecular sieves in the pump, in some apparatus. Exactly same sieves we have converted this MOF, some techniques, and we use some binders to do that. And when we perform the CO2 capture measurement, we found that the MOF has exactly same CO2 capture when it is in gram scale, when it is in kilogram scale, and when it is shaped. So this is very important, that when so we claim in a very small scale. In our lab, we just prepare a chemical in milligram scale, and then we transform this chemical to gram or kilogram scale. But we don't say that how the performance is behaving. So in this case, we check the performance when we transform from gram to kilogram scale. The performance should not decrease, and it is very good. The performance doesn't decrease. So high space-time yield of this MOF, it has 185 kilogram per meter cube per day. This is very important to have high space-time yield. That means you can produce more and more MOFs or more and more compounds per day. Another MOF which we have synthesized and optimized for large-scale application in our lab is MIL53 series. What is this MIL53? MIL53 is nothing but reaction between aluminium 3+ with BDC, 1,4-BDC linker precursor. So this precursor we can synthesize with different functional groups, and we can have different MOFs. Okay, so that's why we call it MIL53X. So when it is synthesized in reflux in water, the as synthesized MOF has some unreacted linkers. And when it is removed, the unreacted parts are removed, activated, we can have the MOF which is ready for CO2 capture application. But as I told in the beginning of my introduction, then MOF can have breathing behavior. This MOF has breathing behavior. Like you can see, this MOF can transform from narrow pore to large pore, depending on the stimuli. So when there is a large pore, when we apply vacuum, the solvent sitting or the gas sitting inside the pore are removed. The moment it is removed, it goes to narrow pore. So this is the breathing behavior. And fortunately, this breathing behavior you can see through powder X-ray diffraction. So this is very important to know how powder diffraction works. So from powder diffraction peaks, you can understand the position of or the d-spacing of any material. From the d-spacing, we can understand that if there is a narrow pore, so the d-spacing between these two layers will be reduced. So there will be shift in the peaks of the powder X-ray. And when it is in large pore, the d-spacing between these two layers will be increased. So it will shift to the left side of the 2 theta angle. Thus we can understand that there is a breathing behavior of a MOF. Coming to CO2 adsorption studies of the MIL53, so with different substitution of MIL53, you can see the amino group, this amino has very good CO2 uptake at low pressure, which is our area of interest. And when we calculated the CO2 N2 selectivity, the MIL53 amino has very high selectivity towards CO2 over nitrogen. And the composition of CO2 N2 is exactly to flue gas. It's like 15% CO2 and 85% nitrogen. When we have done a breakthrough experiment where we mix CO2 N2 and pass through the column of this MOF, so we can see the column is able to hold CO2 for 500 seconds, but it is ejecting nitrogen. Sorry, I'm wrong. It is holding nitrogen and it is ejecting CO2. Why? as I told you, if you sieve your tea, so the tea particles are held and you separate the liquid tea out of your sieve. So this is exactly what is happening with the mop. So we have done different cycles. I am not going to in these details of this study, but in this case, I would say the MOF which is having amine functionality is having better CO2. Why it is so? So just recall, I have told that amine solutions are good for CO2 capture. So this nitrogen having a lone pair can interact with the carbon dioxide. The delta positive carbon of the carbon dioxide interacts with the lone pair of nitrogen. That's why it has better CO2 compared to others. So here it comes. When you fine tune the MOF, you can tune the property and you can tune the selectivity of a particular MOF for CO2 capture. This is a very good example. So when we went for larger scale synthesis, we synthesized in 500 gram scale in our lab. And you can see this is a reactor where we synthesize. This is 5-liter reactor, but we have a 30-liter reactor also in our lab. I'll show in subsequent slides. And when you see this PXRD, so the small scale in milligram scale, you see the PXRD is like this. But when you have larger scale, you see a smaller peak here. This is because of the flexibility of the MOF. And this MOF is going to large pore configuration. So when we did the CO2 capture of this particular large scale MOF, we saw a small difference in CO2 uptakes at low and high pressure. This is because of the presence of large pore. And we have identified another important phenomena that with change of particle size from small to large scale, smaller particles give large pore configuration than larger particle in synthesis. So I won't go in details of these results because these are very much chemistry, but overall the large scale has very good performance as the small scale has. And it has a space-time yield of 140 kilogram meter cube per day. Again. I don't know why it's stopping every time. Sorry for the delay. Okay. Then comes the shaping. So shaping is very important. As I told that you cannot use the powder in the power plants or in this kind of places. So shaping is very important. And we shaped our MOF with different binders, and we identified bentonite with 10% bentonite via wet granulation. And when we shaped these MOFs, we obtained different quantities. And this is very important to check how the beads are stable, the strong in presence of pressure. So you can see they have very good strength in presence of pressure. Okay. So this is very important, but this MOF suffered one problem, that when we expose this MOF to humidity, the CO2 performance decreases. This is a drawback of the MOF. So with this drawback, when we were thinking about how to have a MOF which doesn't decrease their performance in presence of humidity, we came to this MOF, which is MIL 120. Again, MIL 120 is a very simple MOF. It has aluminium, it has benzene tetracarboxylic acid, and when it forms this kind of coordination aluminium chain, it generates this kind of pore, which has a diameter of 4 to 5 angstrom. This MOF has a lower surface area. It has 550 meters squared per gram. It has very high crystal density, and it has high mu2 hydroxyl density, and the metal to ligand ratio is high. So when you calculate cost of a MOF, the most cost is coming from the linker, the ligand. Ligand is very expensive, not the metal. So when you have more metal, that means you are reducing the cost of the MOF. This is what happening in case of this MOF. So from the beginning, we are in advantageous position that we have reduced the cost of the production of the MOF. So this is a 3D view of the MOF. So this is not very predictive structure. This is drawn from X-ray data. We have solved the structure using X-ray synchrotron analysis, and this is how the MOFs look in practical. So these are the aluminum octahedras, and this is the channel. You can see a 3D view here. The CO2 can goes through, and the channel is decorated with hydroxyl groups, oxygen groups. So this provides a very nice polar environment inside the channel, where the delta positive carbon of CO2 can interact with the electronegative oxygen. This is also providing very nice channel. Also, the confinedness of the channel, like the molecular sieving phenomena, as I have told, is helping this MOF to capture good amount of CO2. And another important thing is that this MOF can be obtained in green synthesis in ambient pressure. So we have filed a patent and a paper with this MOF. So isotherm, you can see from the isotherm that at low pressure region, it is absorbing only CO2, not nitrogen. This is the nitrogen adsorption. And enthalpy of adsorption is 40 kilojoule per mole. For your knowledge, this is exothermic process. The enthalpy of the adsorption is an exothermic. It should be negative. But for clarity, for comparison, we always put it positive so that people could understand easily that more enthalpy of adsorption, more difficult to regenerate, less enthalpy of adsorption, there is no selectivity. Moderate enthalpy of adsorption from 30 to 50 is the best material for CO2 capture. So our enthalpy of adsorption is 40, which is very good. When we compare our material to other important materials like CALP20, as I have discussed, which is already commercialized, UTSA, which is in verge of commercialization, aluminum formate ALF, which has been synthesized in National University of Singapore by one of my PhD seniors. This is also in the verge of commercialization. And then these two are zeolites. So if you see that our material is having comparable capacity to this CALP20 and UTSA 16. So our MOF is very good in terms of benchmarking. So it can be commercialized and it can be utilized for CO2 capture. So to understand more about the CO2 capture phenomena, how the CO2 is being captured inside the MOF. So we perform some DFT modeling with the help of Professor Guillaume Moha, who is based in Montpellier, France. So in this one, we identified when the CO2 goes inside, it can orient in two conformations. So one is conformer A, structure 1, and another is structure 2. In structure 1, you can see the CO2 is just sitting inside like this, interacting with the 4 hydroxyl groups. But when it is sitting like in structure 1, it is sitting like this, interacting with 2 of the hydroxyl groups. And you can see the enthalpy of adsorption, which has been written here. So when we compared our simulated adsorption with our experimental one, the structure 1 seems very good matching with the experimental one. So we know that CO2 is sitting like this, not like this. So from here, we can understand when the gas mixture is going CO2 and nitrogen, CO2 goes inside, sits like this, and nitrogen breaks through the porous material and it pures the CO2. So this is further experimentally validated by in situ synchrotron powder experiments, which has been done in European synchrotron beamline in Soleil in France. And here, what we did, how the experiment has been performed, it's a very tedious job. You have to load your material in a capillary, then you have to vacuum it, you have to expose this material to carbon dioxide, and that carbon dioxide, then that capillary then put in the synchrotron experiment, and then after getting the data, you have to solve by Rietveld refinement, which is very tedious. And we have a crystallographer in our lab, this guy Yuri, who is from Russia. He did all these experiments. He's a very good crystallographer, and he located the CO2s inside the framework. And you know, when you want to locate some guest molecule through X-ray experiments, is very difficult because you will have disorder, you will have NPDs, but he successfully did it. And you can see what we have predicted from the DFT model. Exactly, CO2 is sitting like this in the framework. So CO2 is sitting like this and nitrogen is breaking through. So we have a selective CO2 capture material. Selectivity, the predicted selectivity is around more than 100 at different pressure region. And you can see that when simultaneously you put CO2 and N2, very less nitrogen sits inside the pore, but most of them are CO2 and nitrogen is going through it. So from this structure, you can visualize the practical situation when it is exposed in two gas stream. Shaping, this is very important to shape. Shaping of this material we have performed with different binders, and we used silica. Silica gives very nice beads, you can see in this picture, and you can see it is able to hold CO2, but the nitrogen comes out of the beads when breakthrough experiments are performed. And when we perform our breakthrough experiments with 3% humidity, we see that there is a small decrease in the CO2 uptake, but it is not like the previous MOF, the MIL 53. And when we want to regenerate, we just need 50 degree to regenerate the MOF. So when I introduce the CO2 capture and amine solution, I told you that amine solutions are not good because there is the regeneration problem when you have to heat more, like heat at 100 degree or so to regenerate the amine solution. But our MOF needs just 50 degree to heat. So you can see that we can save a lot of amount of energy to regenerate our material. So when we want to test that if our material is good for selective CO2 capture in presence of water or not, so we performed water adsorption isotherm to see. But when we performed, we were very sad that our material is absorbing water at very low pressure. But for CALP 20, it was not absorbing at low pressure, rather it started absorbing from 20% relative humidity. So we thought that it might not work. But when we tested in the previous slide, this curve, when we tested in presence of water, we see that there is a CO2 capacity. CO2 is able to go to be absorbed in the MOF in presence of water. So this is two contradicting phenomena that in one experiment, it is showing that it is not absorbing water, but in another experiment, it is showing that it is absorbing water. So to understand the phenomena scientifically, we performed this operando IR spectroscopy where we have fed the system with a mixture of CO2 and water, a stream of water, a stream of CO2 humid with water. So in this graph, you see when there is CO2 in the initial time, the peak for the CO2 has increased. That means when you have CO2 and water together in the system, first CO2 will be absorbed. So when all the CO2s are absorbed, then you see that the peak of the water is increasing. That means once the CO2 are absorbed, then the MOF starts absorbing water. So this is called kinetic separation. So when you have CO2 and water, it prefers the CO2 over water to absorb first, and then the water absorb. So that means when you take this material to the practical purpose, that time in presence of humidity and CO2, CO2 will be absorbed first. So this can be used for industries for CO2 capture. So after these experiments, we were very happy, and now we know that this can be transformed from academia to industries. And this is how we transform the MOF in a kilogram scale. So in our lab, we have synthesized the MOF in 6 kilogram scale. So this is the reactor we have. You can see it's a complicated reactor, and here is the MOF. You can see we are doing the reaction. So we put all the components here, the solvent and everything in here, and this is a double glass walled reactor. So in the double glass wall, the hot oil flows from this chiller to the wall, and it heats, and it reflux as well. It has a reflux system backside. If you can see, it does the reflux. And this guy is the stirrer or the rotator, which goes inside and stirs the reaction. It's a mechanical stirrer. So you can set the stirring and you can start the heating. And after everything, what you can do, you can connect this bottom part. It cannot be visible, but I can explain. This bottom part with a pump directly to the filtration apparatus. So the pump pumps the solid to the filtration apparatus, and it filters. So it's completely automated. So you program the reaction for overnight, 6 hours, 12 hours as you want. And then once everything is done, you come and turn on the pump. The pumps brings these things through a pipe. You just put the pipe on this Buchner funnel, which is very big in this, and it filters all the solid and the things goes inside to drain. This is how we have done 6 kilogram of MOF. So from milligram scale to gram scale, and now in kilogram scale. And this is how we have attracted the industries. Come see that we can provide you material which can be used for this kind of very high-end application. So this is green synthesis, inexpensive chemicals. This is very important because we have prepared this MOF using sodium aluminate, which is very cheap. And the linker is also very cheap, and it is biosourced linker. The linker comes from biomass conversion of bioplastic. And once we have calculated the space-time yield, we saw that it is greater than 100 kilogram meter per day. Sorry for this is in French, but jour means day. Sorry for this. So we have filed a patent and a paper with this synthesis conditions, and we calculated the production cost. In this graph, I can explain that what does it mean. It means that the energy price and the production cost increases when you need more ligand. But in our material, we use less ligand. So the ratio of metal to ligand is 4:1. 4 metal, 1 ligand. That means we are reducing the cost in the very beginning. So to make a material to go to the industries, you have to think from the beginning that how you are gonna transform, how you are gonna synthesize. Now coming to the pilot tests. So then we synthesize this MOF in a large scale, and then we conducted the pilot vacuum pressure swing adsorption with Professor Guy in Belgium, in Mons, and with the industry. And this is the schematic of the pilot scale testing, where you have different columns, and these different columns are loaded with different adsorbents, and one of it has our MOF. Okay, so when we tested this, I don't want to explain all of this because this is very much engineering phenomena, very much deep in chemical engineering, but I just want to emphasize on recovery and purity of the CO2. So when you capture the CO2 in pilot scale or in any industry, how much you recover after regeneration. So this is very important. So after capture, you take out the material, take out the scrubber, and apply some regeneration process, and how much you recover from that. So our material, we can recover 90% of the CO2 absorbed. And the CO2, when we recover, what is the purity of the CO2? The purity is 93.8%, which is very high. So if I now compare with this, with the amine solution present nowadays in the industry, the amine solution, since it is chemically bonded, it doesn't provide this much recovery and this high purity. Because of the physisorption phenomena, we have this very high purity and recovery from this vacuum pressure swing adsorption. By the way, let me just explain which is vacuum pressure swing adsorption. So this is nothing but you change the pressure by applying vacuum to regenerate the material. That's why it's called vacuum pressure swing adsorption. So this is a very known phenomena in adsorption industries. So in conclusion, I just want to say that our MOF, it has very good CO2 capacity. This is very good candidate for CO2 capture. It has very high selectivity, and it has very good scalability and processability. So the only problem we observed, and then we understood that, okay, this is coming from kinetic separation, is the hydrophilic nature of the MOF. So we worked on this hydrophilic component to make it more hydrophobic. And you can see we have two different strategies. Now we are working on this aspect to make the MOF more hydrophobic. And if we are able to make it more hydrophobic, it will be the winner of the CO2 capture process. And it is gonna beat the CALF 20, which is presently manufactured by BASF and used by Savante. So how we do? So we have used different binders and additive to make it more hydrophobic, to make beads like this. So when you add some binders, you can see we have shifted the water adsorption to some hydrophobic range to the right side, and also chemical tuning of the linker. So if you tune the linker with some hydrophobic material with chemical modification, you can shift the hydrophilicity to hydrophobicity to have this hydrophobic nature in the MOF. So at end, I want to tell you that so not only academic research is very important nowadays, but we should focus on the research which we can transform from academia to industry. And it is very important to work in the interface of industry, because unless you don't know the industries, how they work and how they function and what they need, if you just doing some academic research and publishing papers, it is not going to work, and it is not going to bring some new concept to the world. This is what I have seen during my research career in France or in Europe. I have seen that people always are focused not to publish papers and not to work in the academics, but to think that how can I transform this material or this system to the industry so that in future everyone gets benefited. For your information, I work in ESPCI. My institute is located in ESPCI. And you know ESPCI is very famous for Marie Curie. Marie Curie herself worked in the same institute as I am working now. And I have seen her lab, and I have seen where she worked. Although her things are protected because they are all radioactive, it's protected differently, but her lab is still functioning. And in her lab, there are some instruments still people are working on the instruments. So you can understand how motivated people are here to have a fellow like Marie Curie working in the same institute. She started from very low background, working on radioactivity and giving us the bestest medical treatment, which is called radiotherapy. So when Marie Curie did her research, And when she was recognized by 2 Nobel Prizes, one in chemistry, one in physics, she established Curie Institute. This Curie Institute later invented the radiotherapy for cancer treatment. And she used to travel with a van of X-ray with a radiology apparatus to go to the villages to provide radiotherapy to patients. It was very fascinating to learn her life and to work in her institute. I am very grateful, and I am very fortunate enough to work in her institute. So not only Marie Curie, we have other 2 Nobel laureates from our institute. For example, Pierre Gilles, who worked on gene sequences, which is also very important. So coming to my research, this MOF field is very emerging field, and we could expect a Nobel Prize in coming years. I think in 5 years we should get a Nobel Prize, because how the things are advancing and how people are working dedicatedly. I think it's a very good emerging field in field of material science, in field of chemical engineering, and in field of inorganic chemistry, basic chemistry. So I can give you another example how some of the researchers working in US. So there is a researcher from UC Berkeley. His name is Professor Omar Yaghi. He has developed a MOF which can store water and release water when needed. So what he is doing, he is absorbing water, storing water from humid atmosphere, and taking them off to Sahara Desert to provide water to people. So this is very fascinating. So you can see that we can have nice materials for our society, for our humanity. So with this, again, my computer got paused. I don't know why. Sorry. Every time I have to reshare the session, but I think I'm almost done. Yeah. So I would like to thank my collaborators. So they are my academic collaborators. So we work in interdisciplinary, international collaboration between Europe. You can see it's in France, Belgium, Portugal. We have different collaborators. So these 2 guys, Professor Guillaume and Dr. Dong, they did the theoretical. They always do the theoretical part in our work. Professor Guy and Dr. Nicholas, they do the pilot testing. Professor Daturi and Nuria and Alexandre, they do the operando IR techniques to learn the kinetic study. Professor Pinto, they are from Portugal. Abir and Marta, they do the life cycle assessment and techno-economic analysis. And this is our group which we closely worked. And in this group, we have, rather than me, we have other 2 Indians, Dr. Shamapadanandi, who is now a faculty in VIT Chennai. He worked in this project, and Dr. Mayank Gupta, who is currently working in direct air capture. And I would like to tell you that we have very good professors like Christian, like Yuri, Faid, and George. They are all professors in our Material Institute. So our Material Institute, it's like a small institute inside a university. So in France, you cannot be an independent professor like in India. So you have to have a research director who is Christian, and under research director, you have different assistant professors, and under the assistant professors, we have like research engineers like me, and we have postdocs. So Christian is the director of the Institute of Material, Institute of Porous Materials, and we have these 3 assistant professors who are having PhD and postdocs. Thank you all for your kind attention, and thank you for providing me this opportunity to speak about my research. I think I tried to express my research in a very normal manner, in a very general manner, so that it can be understood by each of everyone who are not from my background or maybe from the different background. But the take-home message is to do some science which can be transformed from academia to industry. Thank you all. Thank you for your attention.
Yeah, thank you, sir. It was really a wonderful and informative session on the
Thank
CO2
you.
capture.
Thank you.
Now we will welcome questions from our participants. So I request participants to ask any questions if there are. Yes, dear participants, if any question is there, you can unmute yourself and ask the question, or you can put your question in chat box too.
Hello, Dr. Debanjan.
Hello.
It was really a very informative session, and
Thank
we
you.
are enough fortunate to have a youngest scientist.
Yes, I'm the youngest among all the distinguished professors you have.
Yeah.
I was very scared because I was thinking that we have this very good list of professors. I might be very niche, but it's okay. I think I have expressed my research work.
We have Rajesh Das with us in this session also.
Okay.
So I have one question for you.
Mm-hmm.
You have synthesized MOF
Mm-hmm.
with aluminum, right?
Yes, yes.
You have explained all scalability, cost effectiveness, stability of it, and connect of it with industry. So
Yes.
have you checked instead of aluminum, you can use other metal and comparative study of this, like
Yes,
copper,
yes.
zirconium?
Yes, the thing is, we have to take into account that what metal you are using and how does it impact. So let me explain in details. So when you do a reaction with other metal ions like copper or something else, this might impact the environment, but aluminum is not toxic. So we always prefer to go with aluminum. We want to go with iron. We want to go with zirconium, but not copper, not cadmium, not cobalt, not nickel, because when you have the side product, if you say, for example, when you do the reaction, all the metals are not consumed. Some of the metals are in the filtration liquid and we dump it. We cannot dump it like that. We have to treat it and dump it. But for aluminum, you can not dump it, but you can just do some less steps to treat it so that you can manage some costs of this life cycle assessment. So we have to think about choosing which metal you are choosing. Okay. And also which salt you are choosing. For example, if you use aluminum chloride, when you do the reaction, the byproduct will be HCl. So now you think about it, in a ton scale reactor, you have ton of HCl, which is very corrosive. So you cannot use something like that. So we always use sodium aluminate. That means when we go for this byproduct, the byproduct is very much soluble in water and it's non-toxic, non-corrosive. So it can be used. So we think all of these aspects to choose our precursors.
Thank you, sir.
Thank you.
Hello,
Hello.
sir. I have one question.
Yeah, please.
Hi, sir, you said that from the chimney, whatever fuel it is coming, you are capturing the carbon dioxide.
Yes,
So
yes.
my question is, from environment, can we capture the carbon dioxide?
Yes, of course. So we have different processes. As I have told, we have post-combustion, pre-combustion, and we have direct air capture. So this direct air capture is capturing CO2 from the normal air, the air we are breathing. So we have materials where it can capture 400 ppm of CO2 from the atmosphere. So I did not discuss because it is out of the scope, but we work on these materials as well.
Okay, sir. Okay, thank you. Because in metropolitan cities in the India.
Yes, exactly.
Yes, sir.
Yes. So this is what, like, we have some investments from company in our lab where they want to develop a material for direct air capture. Like we just put our material in a room, it will absorb the carbon dioxide and also it will absorb VOCs, volatile organic compounds. So like formaldehyde, like this is which is causing the pollution mainly. So this is
Yes, sir.
this is what we are doing, but I didn't discuss in my slide because it will be too long otherwise.
Yes. Thank you, sir. Thank you.
Thank you. Thank you.
Debanjan, am I audible?
Yes. Yes, yes, you are.
Let me ask one question.
Sure, sure.
You have told me that ammonia, NH3, when is combined with the CO2, then just acid-base interaction is there, na?
Exactly, exactly.
So if we want to substitute the amine by the N-methylamine, so that you can plus high effect specificity will be increased. So
yes,
would it be applicable in this case?
yes, of course it will be applicable, but you have to think about this as well. So let me go to one of the slides so that you can understand. So let's say, for example, this guy, this okay. So if you see this one, the MIL53X, so the substitution, when you substitute in a bulkier group, what it will do, it will reduce the pore size in such a manner that CO2 will not go inside. So it will block the CO2. So this is also very important to have a particular pore window. If you close the window with the more bulkier groups, then it's useless also.
Okay, so both these facts must have to be considered. Eh?
Exactly, yeah.
Okay. Okay, thank you.
Welcome. So I can see one question in the chat. Which technique used to quantify captured CO2 as captured carbon dioxide? It's not. So what I have discussed, it's not to quantify the captured carbon dioxide. It's rather already quantified in the stream that it has. So the pre-combustion has like 20% CO2 and 80% hydrogen. Post-combustion has 15% CO2 and 85% nitrogen. And direct air capture, it has 400 ppm of CO2. So it's already quantified. And when you capture and when we do the recovery and purity studies, we can say, okay, we have recovered 90%. So like that we quantify, but this is what we quantify. This is how we quantify. So it's rather than capture process than quantifying the CO2.
Okay, sir. I think there are no more questions.
Thank
So
you.
it's time for a vote of thanks. So on behalf of everyone here, I extend my sincere gratitude to Dr. Debanjan Chakravarti for his enlightening session. So I think, sir, your research in MOPS and CO2 capture has opened up new perspectives here. So thank you, sir.
Thank you. Thank you. Thank you very much for providing me this platform to speak to you.
Yes. Okay, so a big thank you to our enthusiastic participants for their curiosity and engagement. I hope you all found these sessions very informative and enriching your knowledge. So thank you all. So tomorrow is 26th January, which is Republic Day of our nation. So I wish happy Republic Day to all of you. And on Monday at 6 o'clock, we'll resume. So see you friends on Monday at 6 o'clock. Thank you.